So we're streaming.
The stream is on.
And is the owl working for video and audio?
So on Zoom, it's plugged into this. So just go to Zoom and then go to
So we're streaming.
the stream is on. Great. So the meeting owls for the audio check video as well.
And is the owl working for video and audio?
So on Zoom, yeah, it's plugged into this. So go to Zoom. Testing.
Hi, everyone. If you can hear us online, would you give us a thumbs up?
Yeah, I can see and hear you.
Oh, perfect. Great.
Right on time.
That's very blue. Holy.
Well, let's log out of my YouTube so people don't have to see that I was watching trailers of Beverly Hills Cop 4.
Okay.
Sign out to the top, right? You want to do that?
Where is it?
Top
Oh.
right. It's right under where LN is, like.
Sign
there.
out. That's mine, sign out. Yours.
You should just be able to close that, honestly.
Let's sign up, but we can go back to the YouTube live stream. And we can just search for Vanderbilt. It probably won't even be necessary, but maybe someone should keep an eye on the screen.
Yeah, close that. It's already broadcasting.
I would like to keep this open because the authentication, it's good to have this on.
Okay.
So that they might remember something.
Let me
This
check.
was unnecessary.
I'll check the Vanderbilt stream again.
Yeah, thank you.
That's the YouTube channel.
Vanderbilt is strongly.
Yeah, it's working fine.
think everything is going well. Yeah.
I'm in touch with Raina, so if you need something, just let her know. And
Thank you so much.
absolutely.
What, do we know what's happening for lunch?
No, I'll give her a call. So, I'll be back over. Okay, I'll check with her. So,
Then, tomorrow we just need to arrange one of the students to be here, same time-ish to.
okay,
off.
okay, that's great. Maybe we'll have them today, some drinks and all. So I know there's some access to get the drinks.
Mhm.
But I'm making a list of what we can do to make it easier for people.
Do we know, where the nearest, like, filtered water fountain is? Because I know there's a faucet in the data center.
Yeah, let me go look. Oh, in the hallway.
While also after getting stuff. No, I made the dish. Yeah. But when, so, or, you know, Yeah, I mean, I got it today. My name is no, no, I didn't walk in right first. Where Alex. More people. I mean, on in the my channel in Frankfurt. I all of it over. Yes, originally I had my neighbors. But they were not right. It was expected. Now I got why not that? This is rare. It's like, okay, so it makes that because what they do is push up the window. It does that, and I great. Yeah. Okay, so not like convert. Yeah, they're using conversion. That's what. Exactly. They are, yeah, this is not. But you know, you really much. Don't doubt. Whoa. Wow, I mean. Wait, the next question is, yeah, I think that bill here. It was already here. So it's on the second floor, but please. Yeah, take on that. It's not like that. But so like I'm on the second floor. Yeah. Yeah, you just walk out and I'm like, hey, oh my God, the worst thing ever. What the hell? I just have to sit there and wait and see what happens. And no, God. So basically, we should just put up to the top. At least you buy all of you things and then. That was the first time. Oh, weird. Cheers. Right. I wouldn't go to that. Do that, but have. Or have another. Yeah. And I can guarantee you, and I don't think I can take two down. Well, thank you for your attention.
All right, everyone. So we've still got a few minutes. I'm going to give some introductory remarks just to give you some logistics. We'll get started properly with the first lecture, which is me at 9:30. But first of all, thank you very much for coming. It's really the second time we're properly doing this Pulsar Timing Array Summer School. Last year was joining forces with our EMIT program here. EMIT is Establishing Multi-Messenger Astronomy Inclusive Training. So we will have some exercises related to that today for networking at the end of the day, but we're going to get straight into tensor calculus, which is the fun thing to do on a Monday morning before networking. Some logistics, first of all. I just pinned information about restrooms. So just verbally go out of these doors, walk past the elevators, turn right and right again. It'll look like there's nothing there, like it's an empty alcove with just a window. But if you walk down to the window, you will see that there are restrooms and there are water fountains. For other things like Wi-Fi, EduRoam or VU Guest are solid options if you have access to EduRoam. If not, VU Guest will work just fine. And then for the schedule, this is what we have today. So it'll be an introduction to gravitational wave theory today. And I'm afraid that is going to be tensor calculus. So if we don't get through all of the material today, then I've made the notes available on the GitHub repository. The GitHub repository, if you're looking for it, is right here. So it's bookmarked in the school channel. People are starting to add their materials already. We'll have a software help desk today, if necessary. This is for people that haven't really set up their machines to work with PTA software. So there are some instructions here for Linux, for Mac, particularly for Apple Silicon, which is a pain in the neck. And for Windows, I think that's a little bit more custom. So it's using WSL. If you have problems with this, there are experts in the room who have encountered probably the exact same problems as you. So we'll go around and have a software help desk today, just to make sure everyone is set up with what they need in order to access various tutorials and code later this week. What else? Yeah, so on the schedule, we're also going to have Jani. He's another professor here who's going to give an overview on gravitational wave detectors across the spectrum. So we're focusing on PTAs in this summer school, but that doesn't exist in a vacuum, and we want to see how it's in the context of the wider spectrum of gravitational waves and the detectors that are targeting them. Here's that software help desk I mentioned, and then we'll have some introductions, networking, and DEI exercises towards the end of today. You can see the kind of flow of the summer school. We've got really starting from the theory of gravitational waves, then into the kind of detectors we use, which are pulsars, and how we time pulsars. I will actually give an overview of how pulsar timing responds to gravitational waves. So usually that's just given as an equation, but it's interesting, I think, to see how you go from looking at the arrival rate of pulses to seeing how gravitational waves actually influence the arrival rate of those pulses. Then Nima, who's at the front here, is our tech wizard, is also going to give an intro to frequentist and Bayesian inference. A lot of what we do requires statistical techniques that are powerful and fast. And so Nima will talk about that. And then for the actual numerical implementation, Cal Gersbach, who's at the very back of the room where waving his hand maniacally, is going to have a tutorial for you all to work with. Wednesday, I'll talk about stochastic gravitational wave backgrounds generally, how we actually quantify stochastic gravitational wave backgrounds, what stochastic actually means. Then Nima will give a tutorial on using Enterprise, which is our kind of flagship PTA analysis software. William, who's currently stuck somewhere in Canada, I think, will be back. We'll be back on Wednesday and we'll give an overview on how we conduct Bayesian gravitational wave background searches, parameter estimation. And then Kyle again will talk about frequentist gravitational wave background searches using something we call the optimal statistic. But then we kind of move away from the gravitational wave background and get into the next big milestone for our field, and that's going to be individual supermassive black hole binary signals. So Jesse Runno, who's another professor here, will talk about supermassive black hole binaries from a theoretical perspective, how they might come together, how they might evolve to the stage where PTAs could measure the gravitational wave signals. We'll then have a virtual talk by Luke Kelly, who's the architect of the holodeck suite. So I've joked about this many times, but we have a Star Trek problem. So we go from Enterprise, and then our simulation software is called Holodeck. Holodeck really is the premier supermassive black hole binary population synthesis software for our field. It's what Nanograv used, and it's very open, so people are still developing it to put all the bells and whistles in there for binaries. And then I will give an overview of the signals we can expect from individual sources from a theoretical standpoint, equations, etc., and things we have to consider. Then Paulina, who's a graduate student here, will give a virtual talk on basically a tutorial of how we search for them. So it's all well and good knowing how they work in theory, but you will actually get to grips with the tutorial, which will let you search for individual sources in realistic format data. This has only really been possible, at least in the 2-day format, within the last couple of years, because of some analysis speedups, and Paulina will talk about all of those. Notice that her tutorials are spread over Thursday afternoon and a Friday afternoon. That's because we want to give the opportunity for the code to run. So perhaps when you get back on a Thursday night, you can set up your laptop and just let it run overnight, or as long as it needs to get some analysis finished for the search for single sources. Friday, we'll then talk about the kinds of electromagnetic signals we can get from supermassive black hole binaries. We are trying to make multi-messenger detections of supermassive black hole binaries. So we're looking at the EM signal come from those. Then Andrea Mitrodati, who's the co-chair of the Nanograv New Physics Working Group, will give a talk on cosmological gravitational wave signals. It's not just supermassive black hole binaries, it's also possibly signatures of the early universe, primordial gravitational waves, phase transitions, cosmic strings, all of that good stuff. And that's a very active area of research as well. We'll loop back to Paulina then, who will wrap up the tutorial, letting you search for single sources. And I think that's where we'll end, because that's really the biggest area of research and inquiry at the moment in the field. We're confident that we see this first evidence of the gravitational wave background. We're starting to do parameter estimation. We're trying to pin down the conditions under which the supermassive black hole binaries could give this population and give a gravitational wave background signal. But now we actually want to find individual sources, find the galaxies in which they might be coming from, and then say something else about the galaxies and potentially find direct multi-messenger signatures, EM signatures of those sources. So my particular goal for the next 10 years in this field is that we find a single source before LISA does, find a massive black hole binary before LISA does. And that's a ticking clock because LISA is going to launch in 2035. But that means you're well placed in this field to make a big impact and to help us with this search, particularly people like Nikita in this room who are actually leading the targeted searches for single sources. So I think I've rambled on long enough for introductory material. If you need any more information, check out the pinned notes up here. Obviously, you all made it here fine, so the directions worked. Later today, we'll do some speed networking. We'll go through introductions. If you haven't put a slide to introduce yourself to everyone else in the group, and that's organizers as well, please go here and just drop in a slide. It can be very fun. Oh, lots more people about it. That's great. All right, so we'll go through those today, and we're going to do an exercise called Forward. Some of you will have done this before, but Forward is basically introducing yourself to the group using family, occupation, recreation, and dreams. So we'll go through these slides. Everyone will do a Forward, and then if we have time, I think we could probably split up, rearrange some tables and chairs, and do some speed networking, just one-on-one, and then we'll switch every few minutes so you get a chance to cycle around everyone. All right. Any questions at all before we get going? All right. And there's coffee, water, soda at the back of the room. We'll break for lunch at 12:30. Lunch is provided. If you're having any issues with dietary restrictions, and we should have taken all of that into account, but if you find that things are not taken into account, just let me or one of the organizers know, and we'll figure something out. All right, I think it's time to get rolling. We'll maybe take a 3-minute break just in case people want to use the restroom facilities that they've now become aware of. And we'll get going with gravitational wave theory. I'm going to do this pretty much actually writing, or at least highlighted notes that I've previously written. So it's not going to be nice and LaTeX or slides or anything. You're actually going to see my scrawled GR calculus. But I think this is a good way of seeing how you get from the Einstein field equations down to actually a gravitational wave equation, and then the kind of sources we get from gravitational waves. So we'll get started at 9:30 exactly. Take a few minutes break or get accustomed with the room and facilities. We'll be back soon.
Right.
What you codes? Oh, I can just make you from the Zoom. Yeah. Maybe Nima can do it. Can you make Kyle a co-host as well? Yeah. I think you might need to be signed into your Vanderbilt. Hold on.
We can do it after your lecture.
Yeah. Oh, wait, okay. There you go. Cool. Okay, everyone, I know some people just arrived, so I'll reiterate a few of the details. We've got coffee, water, some soda at the back of the room. If you need Wi-Fi, there's VU Guest or EduRoam, and then restrooms. The detailed instructions are pinned in the Slack, but go out past the elevators, turn right, right again, and you'll see water fountains and restrooms. So this first lecture is starting really from basics. Put everything in context we'll talk about this week. This is the theory of gravitational waves, how we get in gory detail from the Einstein field equations all the way through to a wave equation. If you've not taken GR before, if you're unfamiliar with things like index notation or tensor calculus, that's fine. So follow along to the best that you can. These notes are exhaustive, so you can try to follow along in detail later on if you like. They're already up on the GitHub repository for you to take a look at. But what I'm going to do now is talk you through the logic of the different steps, how we get from this thing, this very nice compact thing here, which is the Einstein field equations, all the way through to actually having waves. And these are waves in the geometry of space-time. They're not waves through a medium. They're not like sound waves necessarily. These are actually waves in geometry. Can everyone hear me at the back of the room? I don't need to mic up, do I? Okay, great. I assumed since this was a chapel that it would have good acoustics. So first of all, this thing here gets a special name. That's called the Einstein tensor. All of the information about the geometry of space-time that gives gravity, that gives gravitational waves, is encoded in that Einstein tensor. And it's really it's a shortened form of something that we'll see very soon down here. So on the right-hand side, everything that will source the gravitational waves or source gravity is over here. So these are just some constants, pi, Newton's G, speed of light. This thing here is called the stress energy tensor. So all sources of energy, all sources of matter, energy flux, momentum flux, it's all in here. So sources on the right-hand side, geometry on the left-hand side. You can kind of see the cyclical nature of these equations because you get space-time telling matter how to move and matter tells space-time how to curve. Okay, so it all feeds back in this kind of non-linear relationship between matter and space-time. That quote that I just said is from Wheeler, very famous scientist and relativist. Matter tells space-time how to curve, space-time tells matter how to move. So this Einstein tensor here is really just this thing. So this is called the Ricci tensor. This is called the Ricci scalar. And this thing here is important, and that underlies everything. That's the space-time metric. So that thing is really responsible for defining the geometry of this space-time. If we were in flat space-time, no curvature at all, it would be trivial. We would have this kind of tensor here. So this is Minkowski spacetime or flat spacetime. It's spatially flat, okay? That's why we call it flat and put it in quotation marks. So if we were just dealing with flat spacetime, this thing would be directly equal to this. And if we looked at all of the components of it, we would just have -1, +1, +1, +1 along the diagonals. There'd be zeros everywhere else. So that's the metric of special relativity. It's the metric of flat spacetime. Throughout, if you see Greek indices or Greek letters like this, those are going to run from 0 to 3. That means they'll run over the spacetime coordinates, time, x, y, z, or whatever. If you see Roman indices, A, B, I, J, that's going to run over probably spatial indices, so x, y, z. All right, so if we have flat spacetime, or basically flat spacetime, but we allow there to be a very, very small perturbation in the metric, we'll call that h mu nu. This perturbation is incredibly small, and that's important because we're going to linearize all of our equations. We're essentially just going to do a Taylor expansion of everything, including the Einstein tensor and the stress energy tensor. So this is how Einstein originally derived the form of gravitational waves. One of the first consequences of him having the full field equations was in 1916, he just linearized everything. It's the simplest thing you can do. And that just means we're expanding to leading order. So there's an important convention that we'll use. Usually when we're dealing with these indices for tensors, we'll have indices that are on the bottom. We could also have indices that are on the top. In GR, if we want to move a lower index to an upper index, then we can do that using the space-time metric, this thing here. Oops. This thing here. But since our geometry is basically just flat space-time, we can accomplish pretty much the same thing by using the flat space-time metric. So if we want to raise or lower indices, then we're going to use the flat space-time metric. If this is unfamiliar, that's okay. It's just a detail. So the only exception to this will be when we want to raise the indices on the space-time metric itself. So if we want to turn g mu nu into g mu nu at the top, we're going to take the inverse of that, and you'll see that I'm just doing effectively a Taylor expansion, okay? If I do n mu nu plus h mu nu to the -1, then if I do a leading order expansion, I'll have n mu nu minus h mu nu plus terms that are order h squared. But we're saying that this metric perturbation is very, very small. So throughout, we're going to completely ignore any terms that are order h squared. H squared will be very, very tiny. All right, so I'm going to hit you with it. Here's how we linearize the Einstein tensor. It's tedious. We won't step through absolutely everything, but it's not difficult, okay? It's really just bookkeeping. It's keeping track of indices, of which there are many, but if you keep track of it, then it's a very mechanical task. So the Riemann tensor, of which we derive this Ricci tensor, is defined like this. There are lots of things that we haven't talked about in here yet, but notice that this thing has 4 possible slots, 4 possible space-time indices, the mu, nu, and the delta. There's a thing here called gamma. The gamma is known as connection coefficient or a Christoffel symbol. Basically, this Christoffel symbol here appears in the geodesic equation that describes how objects fall in curved space-time. So it would be a correction to just having acceleration equals 0. So in curved space-time, acceleration is not just equal to 0. You've got corrections to that that tell you how paths are curved when you're in the location of some sort of energy field or matter field. So this thing is going to tell you how paths are curved in space-time, and we're taking derivatives of this. Okay, so when I write partial with a mu here at the bottom, what that really means and what it's a shortened form for is partial derivative with respect to x mu. All right, so I've got partial derivatives of these Christoffel symbols, and then I've got products of these Christoffel symbols. Let's see what these Christoffel symbols actually are. Well, they're further derivatives. They're derivatives of the space-time metric. Okay, the space-time metric is that thing that encodes the geometry of the space-time that we're in. It's not that difficult. We've just got some partial derivatives. So here we've got partial derivative with respect to x mu of terms in the space-time metric, and we're just basically permuting different indices here. And notice that I've got one of these where the space-time metric has the indices in the top position. If there are any questions, anything I can clarify, just raise your hand. I'm happy to do to discuss things while we're doing it. Okay, so we've got our Riemann tensor. The Riemann tensor, if you want a physical understanding of what this thing actually tells us about, it tells us how geodesics, which are free fall paths, will diverge when we're in space-time. Okay, so imagine we've got two spacecraft which are very, very close together, but still spatially separated in orbit around the Earth, and they're falling. Okay, they're falling radially towards the Earth. They will start out pretty close to each other, and then as time goes on, those free fall paths will start to come together. Okay, we're starting to converge towards the center of the Earth. And if we want to actually understand how that works, how these free fall paths will converge or diverge, then the Riemann tensor actually gives us that information. So it's got more information about the geometry of space-time. All right, so now our job, since we've got this Riemann tensor in terms of these Christoffel symbols, and we know what these Christoffel symbols are, we need to linearize that. All right, so if we linearize this, we're just going to approximate for now that space-time metric with the indices above, it's approximately Minkowski space-time, flat space-time. So I can replace the G with the eta here. And remember the coefficients of that, if I were to write down all of the different components of this in a matrix form, it would be -1, 1, 1, zeros everywhere else. And now if I just take the derivatives that I have to do of the space-time metric, well, remember we're saying that the space-time metric is flat space-time, which has constant coefficients, the -1, 1, 1, 1, plus a very, very small perturbation, h mu nu. So when I take partial derivatives, the flat space-time part just differentiates to 0, and I'm only left with partial derivatives of the h mu nu. And then I'll have some corrections here, corrections that come from expanding this out. So remember, I said above here that g mu nu is approximately n mu nu minus h mu nu. But that will just give me terms that are order h squared. And again, we're just linearizing. We're just taking to leading order. Everything that's h squared and above just gets thrown in the trash can, okay? So that gives us our first building block, which is the linearized form of the metric perturbation. I think I'll make the participants list smaller. Maybe that makes that larger slightly. Okay, if you're not going to catch all of the indices, and believe me, I would be amazed if you did catch all of the indices in this kind of truncated session, that's fine. You can follow along in the PDF afterwards, or during if you like. So remember, we've got our Christoffel symbols here, which are now linearized. We go back to our Riemann tensor. The Riemann tensor here had derivatives of the Christoffel symbols, but it also had products. Okay, we had gamma terms. It looks like if I take the product of gamma with another gamma, I'm just going to get terms that are going to be products of derivatives of the metric perturbation. That's going to give me terms that are quadratic in H again. Okay, and we said that anything that's order H squared and above gets ignored. So when we're doing our expansion, our linearization of the Riemann tensor, we're just going to ignore these guys here. So these last two terms, the products of Christoffel symbols, just get ignored. We don't have to consider those further. Our job now is to do this. Take the partial derivatives of these linearized Christoffel symbols. And that's what this is, okay? So I'm taking my Riemann tensor. I've decided that I'm going to lower one of the indices. So we had a description at the start, which looked like this, where the last index was at the top. If I want to bring that last index to the bottom, then I can just use this metric of flat space-time. If you're unfamiliar with index notation, and I haven't said this explicitly, but if you see repeated indices like this, that means there's an implicit summation. So what's not being written here is something like this. Okay? So that's the kind of shorthand of Einstein notation, is that whenever you get repeated downstairs and upstairs indices, that implies there's a sum taking place. Anything else is called a free index, and a free index has to be preserved in its location on the left-hand side and the right-hand side. So I've got repeated epsilons here. That means there's a summation, but then I've got free indices, which are mu, nu, gamma, delta, and I've got a mu, nu, gamma, delta here. So free indices have to be preserved on the left-hand side, the right-hand side. And if you see repeated lower and upper, that's a summation. So now it's mechanical, and I don't think it's that helpful to actually go through every single mathematical term here. But this is what I have to do. I've got these two terms of the Riemann tensor, which are derivatives, partial derivatives of the Christoffel symbols. We had those other two terms, which are products of gammas, but we said that we could throw those away because they're going to involve quadratic in H terms, which are very, very small. So if I actually take the linearized form of the Christoffel symbols and I plug in here, I'll get terms that look like this. So I've got repeated partial derivatives now, second derivatives of the metric perturbation. The form of the Christoffel symbol itself just had a single partial derivative of the metric perturbation, but now I'm taking derivatives of the Christoffel symbol itself, and so that'll give me two derivatives of the metric perturbation. So this means, if you want to see what this means, that means partial something like that. Okay, it's just a second derivative. And looking out at all your faces, I'm just going to skip the math because it's mechanical. There's nothing very physically enlightening other than let's chug through the math, make sure that all of the indices are where they need to be. That's half the battle here. That's most of the battle, is just making sure that the indices are in their correct spot. And if you've got free indices, make sure they're preserved on left and right. If you've got repeated indices, but they're lower and upper, that means a summation. Sometimes you can introduce just what we call a dummy index so that you don't get confused. A dummy index is just a summation variable. So sometimes we'll just arbitrarily change the epsilon to something else. I don't know. Let's call it a phi. Doesn't really matter, it's just getting summed over. It's not a physical index. The physical indices are the mu, nu, gamma, delta. Okay, so I'm plugging in what I had for my linearized form of the Christoffel symbols, tidying things up a little bit, getting rid of terms that just trivially cancel out, and I get to this form for the Riemann tensor. It involves second partial derivatives of the metric perturbation. There are four terms that are like that, and they're only different by the indices being switched around. That's why it's so fiddly, because you have to keep track of everything. But we also have terms here that we're just ignoring that are order H squared. That at least gives us the Riemann tensor. Okay? That's not so bad when you get it into this form, partial derivatives of this metric perturbation. Unfortunately, we don't really want the Riemann tensor itself. What we want are these things here, the Ricci tensor and the Ricci scalar, which are related to the Riemann tensor. So now that we've got this Riemann tensor in this form, we need to get the Ricci scalar and the Ricci tensor. So the Ricci tensor, which was that first term in the Einstein tensor, we need to take the Riemann tensor and basically just repeat one of the indices. By repeating the indices, we're doing this summation, and that means we can just get rid of it. It's implied that it's summed over. Okay, so we take the Riemann tensor, we change one of these, which is usually a delta, a free index, we change that to a gamma, and then we just sum over the terms in the Riemann tensor. We internally sum over those slots in the Riemann tensor. And that gives us a contracted form of the Riemann tensor, which only has two indices, right? Because we've repeated two of the indices in the Riemann tensor, we're left with only two that are actually free indices. That gives us R mu nu, which is called the Ricci tensor. When we do that, and we chug through all of the math, we get terms that look like this. You'll notice that I've got now things that look like just H. H is where I've taken the metric perturbation, H mu nu, it's got two slots. I raise up one of the indices, and then I repeat it. And that just internally sums over it. What that means is, when you get a term that looks like this, that means I take the trace of the metric perturbation, summing along the diagonals, okay? So that's really only relevant for something like this. So I get this somewhat compact form for the Ricci tensor. Now I need the Ricci scalar. That's getting rid of all of the indices and just turn it into a scalar thing. So as you might guess, since I repeated one of these indices, which got rid of two of them, let's repeat this index. It's going to get rid of all of them. Okay, so I'm just going to take the Ricci tensor, this thing here. I'm going to use my flat space-time metric to raise up one of the indices. And then I'm going to repeat that index so it just sums. Everything sums, it turns into one scalar thing. And that actually gives something that's kind of compact, which is just two terms. So I've got two partial derivatives of H, now with things in the upstairs. And then I've got another kind of two derivatives of H, where H is the trace of the metric perturbation. Finally, we're down to a form where we can plug in the linearized form of the Ricci tensor, the linearized form of the Ricci scalar, and then I'm just replacing the metric itself that encodes the geometry of the spacetime with the flat spacetime metric. Because to leading order, this really is just flat spacetime with a tiny little perturbation on top. All right? This is what we get when we plug in all of the terms that are required for the Einstein tensor. So this is the linearized form of the Einstein tensor. It looks gory. It looks like it's got lots of terms in here, but we're going to make a lot of these terms disappear using the magic of choosing a correct coordinate system to analyze our problems in. GR is one of those theories where if you choose an inconvenient coordinate system, then you're just making your life really, really difficult, unnecessarily difficult. So a lot of the battle in GR is knowing how to make terms disappear by just going to another coordinate system. If a term disappears when you go to a different coordinate system, then there's no real physical consequence of it. The laws of physics don't change when we shift from one coordinate system to another. So we can get rid of terms by going to a convenient coordinate system, and that'll leave us with the actual distilled information of the physics of the problem. So we've got our linearized Einstein tensor. We can actually make this a lot more compact by reparameterizing the metric perturbation. And this introduces something we call the trace reversed metric perturbation. So the trace reversed metric perturbation is defined like this. It's h mu nu with a bar written over the top of it. It's not Planck's constants. Don't get confused by that. We're not doing quantum. It's just a bar over the top. And we define that as our usual metric perturbation, but then we subtract off a term that's proportional to the flat spacetime metric itself and involves the trace. Okay? So the reason why it's called the trace reversed metric perturbation is because if I take this thing and I actually compute the trace of it, the trace of this is minus the trace of the original metric, hence trace reversed. And in order to get that h bar equals minus h, I've just raised up one of the spacetime indices with the metric, the flat spacetime metric. That's given me an h. I then got a term that looks like this. If you actually want to do that yourself, do all of the sums in the four-dimensional spacetime. It's pretty trivial because the metric components are -1, +1, +1, +1 along the diagonal. What you'll get is 4 over all of the different spacetime coordinates. So I've got h minus a half times 4 times h minus 2h is minus h. Why have we done this? Because it actually gets rid of a ton of terms, makes our life a lot easier. So if we substitute the form of the trace reversed metric perturbation into our linearized Einstein tensor above, where we'll get our terms like this. So this is the more compact form of the linearized Einstein tensor when we've introduced this trace reversed metric perturbation. And notice I've just, to make the connection, I've put the right-hand side of Einstein field equations here as well. Now it'll be convenient to actually set that to 0. We're going to imagine that we're deriving gravitational waves out in the vacuum of space. They're passing through the space-time that we're in, but we're far away from a source, so we're not going to consider a source quite yet. But this is the form of the Einstein tensor when we do all of our laborious linearization, okay? Laborious, not difficult, so you can do it. It's an exercise to do in your own time. It sounds like a cop-out, but really is useful to do. So this term here is interesting because if we actually think about what this term in the red box is, then it's really just box h bar mu nu. That is the box here is the space-time. This is where my French is going to let me down, the D'Alembertian. It's the wave operator for four-dimensional space-time. Okay, so if I look at this term, actually expand out in coordinates what it is, I'm going to get minus d by dt squared plus d by dx squared, et cetera, acting on h mu nu. So that kind of looks like it's a wave operator acting on our metric perturbation. That's great. I've got all this junk here, though. How can I get rid of those? This is where we start to choose our convenient coordinate system. So we've got something that looks like it's going to lead us down a path to a wave equation, but we just need to make that more explicit by getting rid of these extra terms. We don't know that we can get rid of these extra terms. They might actually be physical. We only know that from history because Einstein did it and it worked out. There are wave solutions and now we've detected them. So it does look awfully like a wave equation. So can we make the other terms disappear? We can. That was. We can introduce something called the Lorentz gauge. The Lorentz gauge is called the Lorentz gauge because there are similarities with similar gauge choice in electromagnetism, where we want to make terms that involve the divergences of our object disappear. So you might be familiar with the Lorentz gauge in electromagnetism, where you make divergences of fields disappear. Everything up here, the junk that we think we want to get rid of, involves divergences of the metric perturbation, the trace reverse metric perturbation. So let's see if we can move to a coordinate system where that's true. Let's imagine we're just introducing a translation of our coordinate system. So we introduce an x primed coordinate system where it's our original coordinate system plus some offset here. We then go through the exercise of transforming all of our objects, like the space-time metric, into this new primed coordinate system. So we end up getting a g primed in terms of our original g, our space-time metric, and that involves partial derivatives of our offset in our new coordinate system. And there'll be terms involving h squared that we're just getting rid of, we're ignoring, as usual. We can also transform our metric perturbation itself, and that transforms exactly the same way as our overall space-time metric, just partial derivatives of our offset. The Riemann tensor itself, that thing R with the 4 slots in it, that doesn't change because that will involve changes that are quadratic in h squared. Again, we're ignoring. So a lot of things can be swept under the rug when we're in linearized gravity. We're only considering leading order linear terms of perturbations. When we do this, when we transform to the trace reversed metric perturbation in terms of our new coordinate system, so we've got a primed here, we get the original metric perturbation, trace reversed, and then we have our transformation, and then some other terms here. In practice, in order to make terms where the divergences of the trace reverse metric perturbation are 0, we want to be able to do this thing here. We want to be able to say that divergences of the trace reverse metric perturbation are 0. And in order to do that in this coordinate system, we need to be able to have that the divergences of the trace reverse metric perturbation minus the D'Alembertian on this offset, on this transformation, are equal to 0. So in effect, that just means we want to move to a coordinate system where the space-time D'Alembertian operating on this offset that we've introduced, this offset in our coordinate system, is equal to this. And what have we got here? We've got 4 equations with 4 unknowns. We can always solve this. We can always find a coordinate system, an offset, where this condition is true. We don't need to specify what it is, but by saying that we've got enough equations, we've got enough unknowns in order to satisfy this condition to take divergences to 0, that's enough to say, let's just ignore that junk. So we need to be able to do this. It's always possible to introduce a coordinate system, a new coordinate system, where that condition below is satisfied, and that condition allows us to get rid of this, to get rid of this, and to get rid of this. Okay, so it's just a clever choice of coordinate system. And that leaves us with something that is a wave equation with a source on the right-hand side. Okay? Let's take a break, because that was a lot. That takes us down to basically how we get the form of the wave equation. Okay, there's a lot of work to get there. We had to linearize the Riemann tensor, get the form of the linearized Christoffel symbols, get the Ricci tensor, get the Ricci scalar, plug it all back in, introduce a new change of variable called the trace reverse metric perturbation, introduce a new coordinate system or gauge called the Lorentz gauge. But it's to demonstrate that it's possible to deal with gravity in the linearized form and get a more intuitive looking equation that is just a wave equation sourced by things on the right-hand side here. Okay, so this is the equation of gravitational waves where this will have a solution that is now a wave solution in the trace reversed form. We don't lose generality. We don't lose anything by writing it in the trace reverse metric perturbation form. But we can solve this now and it will have a wave solution because we've got it in this physical wave form. Any questions before we get on to how we actually source these gravitational waves? Yeah.
What is the condition that this is sort of assuming even you're at? What kind of physical thing you require?
Physically, you're saying that if you're making a tiny, tiny change to space-time, then it's not going to be a change that's of order the background space-time itself. So say you're in orbit around the Earth. The space-time curvature created by the Earth has to be much, much larger than any effect that this tiny perturbation has on the metric. So you're effectively just saying that if you're trying to make gravitational waves and you're doing this linearized derivation, this thing here is much, much smaller as an effect than the actual background space-time itself. So much smaller than the Earth's effect on space-time, sun's effect on space-time, etc. It's a good question. Any other questions online? All right. So often this is shown as a wave in a vacuum. So we're far, far away from a source. We're looking at a region of space-time where we don't have sources. You can have wave solutions in the absence of sources. That's totally fine. So we'll set for the moment, keep doing that. We'll set for the moment the right-hand side to be 0. That makes it trivial to actually get solutions for this. So we've got wave operator on the trace reverse metric perturbation equals 0. The easiest solution to that is this thing. And it's so obviously a wave that we don't even need to look at it further. Okay, this is a wave solution in 4-dimensional space-time. The only thing to worry about here or to be aware of is I've got my trace reverse metric perturbation, I've got my amplitude tensor for the gravitational wave metric perturbation, and then I've got K sigma X sigma. So I've got repeated indices there. So there's a summation where this is the wave 4 vector. So it's like a wave vector, but it's 4-dimensional space-time. And then this thing is really just the position vector in 4-dimensional space-time. So if I were to write out X sigma, it would be like T, X, Y, Z, or oops, X sigma equals T, R, theta, phi, depending on your coordinate system. And K here, the wave 4 vector will include information about the frequency of the wave and the direction that the wave is propagating in. And when you do your summation, it will just look like a propagating wave in 4-dimensional space-time. Finally, another gauge choice that's often made, and this is some terminology you might have heard if you've seen gravitational waves before, we go to the transverse traceless gauge, a TT gauge. And that's just removing some extraneous degrees of freedom. It's important to do this because when Einstein first looked at the form of gravitational waves that he derived, they had many degrees of freedom. And this caused famous scientists to give a little bit of shade against these solutions, including Sir Arthur Eddington, who said that gravitational waves could propagate at the speed of thought. That was just because there were some solutions that could travel at arbitrary speeds. There were some solutions that traveled at the speed of light, physical solutions, but there were some solutions that could travel at arbitrary speeds. And those arbitrary speed solutions were ones that you can get rid of by making this choice to remove extra degrees of freedom in the equations, introducing this transverse traceless gauge. So it's just additional constraints on various indices of the metric perturbation. When you do that, when you go into the transverse traceless gauge, you get this kind of form for our propagating wave. So this is the form of a gravitational wave propagating along the z-axis. And you'll notice if I look at the form here, say this is T, X, Y, Z coordinate slots, T, X, Y, Z slots, you'll notice that while the wave is propagating in the z direction, it has no influence in the z direction. This is a completely transverse wave. All of the influence of this gravitational wave is in the XY plane. So it has similarities with electromagnetic waves. It's a transverse wave, propagates at the speed of light. You'll notice that we have plus and cross here. That's because when we get rid of all of those degrees of freedom that we don't need and boil everything down to the physical solutions, we end up with 2 degrees of freedom, essentially, that give us our 2 gravitational wave polarizations, called the plus and called the cross. And they're named that way because of how they deform the space-time that's perpendicular to the direction of propagation. So, if I look at my plus shape, the gravitational wave here would be coming out of or into the screen. And the little dots indicate that I've got a ring of test masses just arranged evenly apart in a circle. Test masses, if you're unfamiliar with the terminology, just means that they have no effect themselves on the space-time. So they're just kites in the wind. They're just moving along with the space-time itself. They're not creating their own space-time curvature. So if we go through one period of the gravitational wave coming out of or going into the screen, then the gravitational wave will first deform it into an ellipse that's elongated. We'll push it back inwards and then make something that's elongated in a vertical direction. So that's the plus shape, because it's making plus. The other polarization that's actually offset by 45 degrees, not 90 degrees. It's offset by 45, and as you can imagine, when you tilt the plus, you get a cross shape. That's all it is. The reason why the 2 polarizations are offset by 45 degrees is because gravitation is a quadrupolar theory. If you go to the kind of quantum description, then the graviton is spin 2 as a particle. And so that's what gives the polarizations being offset by 45 degrees. That's where it's different from electromagnetism, where you've got the different polarizations that could be offset by 90 degrees from each other. That is the simplest description, simplest way we can write down gravitational waves. Propagated in the z direction, but you can arbitrarily do a coordinate transformation that moves it in any direction you want. And you'll see here we've got omega, which is the angular frequency, multiplied by t minus z. There's no speed in here because it's traveling at the speed of light, and we're saying that c is equal to 1. Sometimes we work in units where g equals c equals 1, because relativists are lazy and we don't want to keep writing things. That's why we introduced the notation, getting rid of the summation symbol as well. Right, I think we've talked enough about the left-hand side of the Einstein field equations that at least gives us the solution to a propagating wave in 4D spacetime. Let's look at the right-hand side. So this stress energy tensor, as I mentioned at the start, is encoding everything that could be sourcing gravitational waves. Matter, energy, and not just the presence of matter and energy, but the movement of matter and energy. So energy flux and momentum flux. If you were to take the different slots in the stress energy tensor and try to peel apart what each of them are responsible for, then the TT part, or the T00 part, if you want to write it like that, the bit up here, that gives the energy density that's in the space-time. And then along here, this part gives the energy flux, the movement of energy. Down here is the momentum density, and this is the stress tensor. The stress tensor is really just things moving along at different speeds and creating some sort of stress or strain. You can think of it kind of like material science, where you have stresses and strains. So that gives an intuitive understanding of what the different components of the stress energy tensor are. But let's actually do a little exercise to see how we can produce gravitational waves from this. So we'll hardly use any of these slots. We'll hardly use any of this information. This is going to be a very simplified form of how we get gravitational waves from a binary system. So how do we produce gravitational waves? Let's look at a comparison between gravitational waves and electromagnetic waves. You might be familiar with moments of distributions. I'm sure you're familiar with moments of forces, but the moments of distributions are how we compute things like inertia and other quantities like that, or even the center of mass of a charge distribution or the center of mass of an actual matter distribution. If we look at the monopole moment, the monopole moment can be written down in electromagnetism as an integral over the charge distribution. The integral over the electric charge distribution is just counting up all of the charges, so it gives us Q. If we take the first derivative with respect to time of that total charge distribution, then it has to be zero. We're bound by physical laws that say charge is conserved. So we can't get electromagnetic waves from the monopole term of the charge distribution. If we look over here, if we look at the dipole term of the charge distribution, the dipole term is the integral of the charge distribution times the directional vector. And that can just be related to, that should actually, I'm going to correct this. This should actually be the total charge. It's total charge times the position vector of the center of momentum or center of mass of the system. If we take the first derivative of the dipole term of the charge distribution, then we've got something which is the effectively the flux of charge. There's no conservation law that's bounding that. And so we can get electromagnetic waves that are sourced by the dipole moment of the charge distribution in electromagnetism. That's why electromagnetic waves are described as dipolar. If you want to generate electromagnetic wave, all you have to do is take an electron accelerator. That will generate an electromagnetic wave. A moving charge will generate electromagnetism. That is a dipolar distribution. Let's look at gravity. We can similarly look at the monopole. Now we're dealing with matter distribution. So we're not dealing with charge anymore. We're dealing with mass or energy. If I integrate the total mass that I've got in a region of space, that's the total mass, obviously, and mass is conserved. So gravitational waves can't be sourced by the monopole term of the matter distribution. Let's look at the dipole. The dipole now for the matter distribution is the integral of rho times this position vector, and that gives total mass times the position vector of the center of mass of the system. If I now take the time derivative of this, that will give effectively the total momentum of the system. And if I take the time derivative of that, that's zero. Because we do have a physical restriction now because momentum is conserved. Now, this is considering something that in physics is sometimes called the electric moment. You can also look at the magnetic moment. You can even look at the electric and magnetic moments when you're dealing with matter and energy distributions, not just in electromagnetism. This holds true when you're looking at the magnetic dipole moment as well. The magnetic dipole moment of a mass distribution is also conserved because that gives you angular momentum. This is linear momentum. This is an argument for linear momentum, that since linear momentum is conserved, we can't get gravitational waves sourced by dipolar moments of the mass distribution. Similarly, angular momentum is conserved, so we can't get it sourced by the magnetic dipole moment either. So effectively, dipole moments, monopole moments of our matter distribution are out for giving gravitational waves. Instead, we need to go to the quadrupole moment of the mass distribution, which looks something like this. So I'm going to write the quadrupole moment of the mass distribution is I, and the ij at the top are going to indicate spatial indices, x, y, z. If I write down the quadrupole moment of my mass or energy distribution, that's just the integral over the space of the matter energy distribution, Ri, Rj. Right, because I've got two of those position vectors now because I'm dealing with a quadrupole, no longer with a dipole. And one can show, and I won't show it here, but it's in a paper from the 60s, that the trace reverse metric perturbation, the actual gravitational wave itself, can be written as related to the second time derivative, the acceleration of the quadrupole moment of a mass distribution. Okay, so we've got our quadrupole moment here, ij, taking two time derivatives. And the other factor here that's important is this inverse to the source distribution, inverse to the source relationship. So gravitational wave amplitudes fall off inversely as the distance to the source. The flux still falls off as distance squared, but the amplitude, just like the electric or magnetic field amplitude, falls off as 1 over distance. So we can do a quick order of magnitude analysis of how we get gravitational waves from a binary system. The binary system is the simplest thing you could imagine that gives a quadrupole moment in a matter distribution. You can consider it effectively as just 2-point masses orbiting each other, same mass, separated by a distance r. And I've got things that are going at mass, things that are going as distance. I can imagine something that goes as time as well. In a binary system, the only physical thing that makes sense there is the period of the binary system. So if I just plug in quantities that have the right dimension here, let's see what we get. We need our quadrupole mass moment. That goes as mass times distance squared. So I'm going to plug in mass times distance squared. I then need a time quantity squared. Let's put in period squared. Dimensionally then, I need another distance quantity, and I'll put in the distance again there. I'm just doing dimensional analysis to see if things shake out. If I cancel out some terms, I'll get m to the 5/3, p to the minus 2/3 over r. And then if I use Kepler's third law, I'll end up with something that's proportional to mass to the 5/3, f to the minus 2/3. That is correct. If we do all the detailed derivation, and we will in a second, you'll see that the amplitude of gravitational waves from a binary system are proportional to the mass of the system to the power 5/3 and the orbital frequency of the system to the power 2/3. We got there just by looking at this formula here and doing dimensional analysis. Okay, so the rest of it is just making things a bit more precise and getting numerical prefactors in place. But if you do dimensional analysis and plug in things that make physical sense and think about what are the different quantities in a binary system, as simple as this, you get the correct scaling relationships. Okay, I think that's a really cool result, so I hope you remember it. It's very useful going down the road. And if I take this relationship and I plug in actual reasonable quantities for the pulsar time in array band, which is nanohertz to a few hundred nanohertz, then the amplitude of the gravitational waves is 1 part in 10 to the 16, roughly speaking. So that's what I mean by very, very small. 1 part in 10 to the 16 perturbation to the background spacetime. That's really big compared to the equivalent metric perturbation that LIGO, Virgo, and Cagra deal with. LIGO, Virgo, and Cagra are dealing with 1 part in 10 to the 21 because they're dealing with much smaller sources and higher frequencies as well. So the balance in that gives 1 part in 10 to the 21. We're looking for binary systems that are sourced by the most massive black holes in the universe. LIGO, Virgo, Cagra is looking for binary systems that are sourced by objects formed from stars. Stellar mass black holes, neutron stars. So when we're dealing with supermassive black holes, we're talking about billion solar mass scale, tens of nanohertz, and then distances, we would hope, of hundreds of megaparsec or so. And this is just, I'm sure you've seen one of these astronomical scaling relationships before, but it's useful to think about typical quantities you would deal with. Now, if you want to see the full gory derivation, it's not that bad, of how you get gravitational waves from a binary system, and we can talk about that next. This just requires a little bit of a geometry setup. So we've got a binary system here. One mass is over here, one mass is over here. I've got my X, Y, Z coordinate system, like this. And my binary of 2 black holes or compact objects or whatever is moving in the XY plane. Okay, so these two masses, which both have the same mass for this exercise, are both in the XY plane. This is mass 1, this is mass 2. The orbit is moving about with an angular frequency of omega. That's 2 pi times the actual physical frequency. And then the orbital separation is 2 times r, or if you like, the orbital radius is r. So in order to compute my quadrupole moment, my quadrupole mass tensor, I'll need to actually be able to write down what the positions of these masses are as a function of time. Again, that's very, very simple because I've just got one mass over here that is moving around in a circle at a radius r. So the x position of mass 1 is r times cosine omega t. The y position of mass 1 is r times sine omega t, and z is always equal to 0. It's always in the plane. If you want to get what the coordinates of x2 are, second mass is just on the opposite side of the first mass, so you just take negatives. So x2 is minus r times cos omega t, y2 is minus r sine omega t. It's that simple, okay? You just got objects moving in a circle. Now that I've got my positions, I can write down what my quadrupole moment tensor is for this mass distribution. Now, the thing that makes this very, very simple to do is that my mass distribution is going to be approximated as 2 point sources. So I'm not going to consider these objects as having any physical extent. These are, for all intents and purposes, point sources moving in space-time. Because they're point sources, that means that the distribution is essentially just a delta function. It's a delta function spike of mass at the positions of the sources themselves. The reason why I phrase it like a delta function is because we can trivially do integrals over delta functions. So you're considering here a mass distribution that's got 2 delta functions centered in the positions of the sources. If I want to actually analyze what the, say, xx coordinate of the quadrupole moment tensor is, that's what I'm doing here, then my ixx is just going to be m times x1 squared plus m times x2 squared. Let's go back a little bit to see why that is. So I know that my quadrupole moment tensor generally looks like this. If I've got a delta function in here at the position of the source, and it's got a certain mass, then when I do the integral is just going to, over the delta function, is going to take the value of the position of the source. So that's why I can do this so easily, because I do one delta function integral for the first source, add on the other delta function integral for the second source. That just gives me m times x1 squared plus m times x2 squared. And then I'm just plugging in what x1 and x2 are. I know that x1 is r cos omega t, x2 is minus r cos omega t. I'll get 2 times mr squared cosine squared omega t, which I can expand out using trig relations and get mr squared 1 plus cosine 2 omega t. Getting to something that has cosine 2 omega t is very, very important, because we can read off almost immediately what the frequency of gravitational waves are in terms of the orbital frequency of the binary. Then the rest of this is sort of a mechanical plugging in different coordinates. So we're just trying to populate our quadrupole moment tensor. So I've got ixx, let's do ixy. That means I've got an m x1 y1, m x2 y2. Chug through all the math, I get mr squared sine 2 omega t. Likewise for iyy, and I get my1 squared, my2 squared. You see, it's very, very simple. Anything that involves the z is equal to 0 because my sources are in the xy plane. But if I then take my quadrupole moment tensor that I've just worked out, the different entries, xx, xy, yy, I then take 2 time derivatives of it. Remember, I have to do 2 over r times the second time derivative of my quadrupole moment tensor, I get something that looks like this. So this is over x, y, z, x, y, z. The influence of the gravitational wave is entirely in the xy plane. I've got nothing here in the z components, but it is propagating in the z direction. And then I've got my amplitude over here. So what can I tell about the frequency of this wave? I kind of gave it away just a few minutes ago, but this is clearly a wave that's propagating with a frequency that's 2 times the orbital frequency of the binary. That is a general result. For circular binary systems, the gravitational wave frequency is just twice the orbital frequency of the binary. Things get a bit more complicated when you've got an eccentric binary, because as you get to higher and higher eccentricity, more elliptical orbits, the gravitational wave emission starts to get spread from just the second harmonic of the orbital frequency into higher harmonics of the orbital frequency. But for circular binaries, this very, very simple relationship always holds. Gravitational wave frequency, twice the orbital frequency of the binary for circular orbits. Now, that gives the amplitude of gravitational waves, but we would like to actually be able to measure and talk about energy emission from a system, particularly when we're dealing with a source like in LIGO, Virgo, Cagra. The systems are clearly evolving. They're not staying at the same circular orbit. The loss of energy due to the emission of gravitational waves causes the orbit to shrink. Sometimes in astrophysics, we call that the orbit hardening. It's getting tighter and tighter. Actually proving that gravitational waves carry energy was the thing in the 1950s that convinced all of physics that gravitational waves were real and not just fake made up mathematical things. There's a very relatively famous thought experiment called the bead experiment, which Richard Feynman came up with, and then other people actually did the math for. But if you imagine you've got a wooden rod with a wooden bead on it that's allowed to move up and down, slide up and down, and a gravitational wave comes in, it will cause that little bead to move along the rod. It's being displaced along the rod. And because that will generate some friction, it's clear that the gravitational wave is putting energy into the system. So the gravitational wave must have carried energy in the first place, right? Because you've got a bead moving along the rod, that'll generate friction, heat. The energy has to be coming from somewhere. The fact that gravitational waves carry energy and can be shown to carry energy physically is what proves in a physical sense that they're real. So how do we work this out? Well, we just rely on what we know about the energy that's carried in waves, any waves. Waves on a string, electromagnetic waves, waves on the ocean, the formulae are all the same. We've got some kinetic energy of the wave, we've got some potential energy of the wave. When you look at that, if you average the power being carried in a wave over many, many orbits or many, many cycles of the wave, you get that the power or the energy flux is proportional to the amplitude of the wave squared, and then the frequency of the wave squared as well. So we're looking for something that is frequency squared, amplitude squared. Let's do an order of magnitude argument here. We've got our energy flux that we want to be quadratic in the amplitude. So it has to be quadratic in the quadrupole moment tensor. Remember, the amplitude of gravitational waves is proportional to the quadrupole moment tensor. But the fact that we've got an omega here, in a dimensional analysis sense, that means we need 1 over time. And we can get a 1 over time by doing another time derivative of this quadrupole moment tensor. So the luminosity, or the energy carried away in gravitational waves, is going to be proportional to the third time derivative. That's what these 3 dots mean, the third time derivative of the quadrupole moment tensor. And the reason why we've got 2 of these is because it's quadratic in the amplitude. So quadratic in the amplitude gives us 2 terms in the quadrupole moment tensor, And then the frequency squared here means that each of those quadrupole moment tensors gets another time derivative. And this line through here just means that we've redefined the quadrupole moment tensor to look a bit more compact. You don't necessarily need to worry about what that is. You can treat it or think about it just as the quadrupole moment tensor itself. And for our simple binary system, if we average over an orbit or average over a wave cycle, that's what these bracket operators mean here, averaging over orbits, averaging over cycles, then we'll get a form that looks like m squared r to the 4 orbital separation, frequency to the 6. And by using Kepler's third law again, which we can absolutely do in this approximation, we get physical factors here, light, Newton's constant, weird factors of 4 to the 3rd, but then m to the 10^3, and then the period of the orbit to the minus 10^3. So that's the luminosity or the energy radiated in gravitational waves from a binary system. If we want to consider how the emission of gravitational waves actually affects the binary and causes the binary to shrink, then we can look at the total energy that's bound in a circular orbit, just the total Newtonian energy in an orbit. That's going to be kinetic energy and potential energy. If we look at the total amount of energy in an orbit, then that's equal to minus m squared over 4r. That's kinetic energy plus potential energy in a binary system. Let's take the time derivative of that. So we're going to allow the energy in this orbit to change with time. And then we're going to equate that change in the energy of the orbit, or the rate of change in the energy of the orbit, to the emission of gravitational waves. So I'm taking the time derivative of my Newtonian energy in my orbit. I'm using Kepler's third law to get rid of things like the orbital radius and put in things like the orbital period. And I end up with the rate of change of the period of a circular binary orbit is negative. That's good. That means the period is getting smaller, the orbit's getting tighter. So the emission of gravitational waves, the loss of energy into gravitational waves from a binary system, will cause the orbit to shrink. And the relationship goes as mass to the 5/3, period to the minus 5/3. If we change this from period into orbital frequency, then we get that rate of change of the orbital frequency goes as mass to the 5/3, orbital frequency to the 11/3. That's a really, really handy relationship to have in your pocket. Knowing that f dot, the f by dt for a binary system, a circular, goes as f to the 11/3. Now, if I'd done all of the detailed math for an eccentric binary system, then you would see that not only does the orbital period shrink, the orbital frequency increase, but the eccentricity of the system will also decrease. The emission of gravitational waves not only causes the orbit to shrink, it also causes it to circularize. So something that starts off very, very elliptical, over the repeated emission of gravitational waves will start to become more and more circular. How do we know this works? Well, it's won a couple of Nobel Prizes. That's not necessarily saying that it's correct, but these are observations of a particular pulsar in a binary system. This is pulsar B 1913 plus 16, first discovered in 1974. So this discovery is now 50 years old. And over decades, it has been observed how this system is evolving. The fact that there's a pulsar in the system and we can time the pulsar, I think we all have an idea of how that works since we're at the summer school, but we'll talk more about it tomorrow. The fact that we can time the system means that we can map out the geometry of the orbit, and we can see that there's a shift in the time to the position of closest approach of the components of the binary system, the pulsar and the other star. If we do the same calculation in GR, then we get this line here. So that's the theory line. These are points with error bars. There are error bars here that you can't see. The agreement between this system and GR is extraordinary. And this gave the first indirect evidence for the emission of gravitational waves. Now, sometimes you'll hear people talk about indirect. I've mentioned indirect. I don't think it's particularly useful to think about indirect versus direct measurement of gravitational waves. I would just phrase it as this system give evidence for the emission of gravitational waves. The first evidence for the reception of gravitational waves came from this system. This is GW 150914, the 14th of September, 2015. And this won the 2017 Nobel Prize in Physics. What you're seeing overlaid here are two signals from two different detectors of LIGO. LIGO, the Laser Interferometer Gravitational Wave Observatory, one in Louisiana, one in the high desert in Washington State. And what you're looking at here is a little bit of noise on top of a system that looks like it's circular, but also increasing in frequency. Okay, as the system is orbiting, it's generating gravitational waves. Those gravitational waves are being emitted, causing the orbit to shrink until eventually you get the merger and you get another phase in here, which we won't talk about. It's called the ring down phase. It's almost like the final black hole is being struck and is ringing like a bell at certain characteristic frequencies. And the frequencies and amplitudes of those modes depends on the mass and the spin of the final black hole that's formed. But this was, roughly speaking, a 30 solar mass plus a 30 solar mass collision. And it formed a 57 solar mass black hole at the end. So 3 times the mass of the sun converted into energy was lost into the universe as gravitational waves in a matter of a few hundred milliseconds. That's an incredible energy flux. Okay. Now take the tens of solar masses that are being considered in LIGO, Virgo, and CAGRA, these other instruments that are doing ground-based detection. You translate that to the billion solar mass scale, the energy flux just gets truly gigantic. And that is all I have for you. I think I've taken you from the year 1915 up to the year 2015 through the derivation of gravitational waves, how we get a wave solution, how we can source the gravitational waves, and how we can establish some physical consequences of the emission and reception of gravitational waves. So with that, I think we'll pause, and I'm happy to take any questions. Thanks. Yeah.
How long usually does that gravitational wave ringing occur after the?
That's a great question. I think it will depend on the mass of the final black hole. So this here is tiny, tiny fraction of a second. This is not even observable yet. There are some groups that think there might be hints of this ring down phase if you stack the events over each other. So LIGO's observed now 100 or 90-ish official ones. And then if I just keep saying numbers, maybe Quran will smile and tell me exactly how many numbers have been found. But it's close to 100 or more. And if you stack events, then statistically, you might be able to pull out evidence for this ring down phase. That would be really, really interesting because it would provide another piece of evidence for the no-hair theorem. The no-hair theorem states that black holes can be entirely characterized by 3 numbers: the mass, the spin, and the electric charge. And for astrophysical black holes, the electric charge can be considered to be 0. So it's just 2 numbers. 2 numbers define the entire characteristics of this phase, mass and spin. So it hasn't been found yet. This would be, tiny fraction, maybe tens of milliseconds or so, that would be observable. Future ground-based detectors will certainly see this. And there's even another step in here that we haven't talked about called gravitational wave memory, where, this is just an aside, but if you look at the gravitational waveform going like this, it doesn't go back to this, just flat. It actually goes back to something that's offset. So there's like a vertical offset in where the space-time metric goes back to. That's called the gravitational wave memory. It's sometimes phrased as the effect of gravitational waves generating gravitational waves, creating a feedback that imprints a permanent deformation on space-time. So imagine you've got a really elastic material, but it's not perfectly elastic. And if you stretch it too much, it will create a permanent deformation. The gravitational wave memory effect in that last stage is sometimes phrased like a permanent deformation. Again, it has not been found yet, but it's a consequence of GR and it should be found in next generation detectors. Tyler, did you have a question?
Yes. Maybe this will be discussed later in the school, but at the end of the nanograph 15-year paper, there's discussion of multiple correlation models for gravitational waves, including discussion of a monopole signal. Theoretically, if gravitational waves are not supposed to have any influence in the monopole, first of all, why was that even something that needed to be explored? And B, why is there, how could there be any, how could that be a favored signal? How could there be any evidence? There's a suggestion that that's not just maybe pulsar noise, but a real signal. So how is that possible given what we just discussed?
Right. So that's a fantastic question, and it actually brings up a point of terminology that is helpful to everyone else in the room as well. So when I was talking about monopoles earlier, I was talking about the monopole of, say, the matter distribution, which looks like that. So that's the monopole of the matter distribution, where the dipole would look like this, and then the quadrupole has another R vector as well. This is different from the monopole correlation signature that is discussed for stochastic gravitational wave backgrounds. When we talk about correlation signatures, and I'll discuss this in detail on Wednesday, for stochastic gravitational wave backgrounds, we're taking two detectors, in this case, two pulsars. We're correlating their signals, and we're looking for a distinctive pattern of correlations in the timing properties between those two pulsars. So if this is the angular separation between two pulsars, and then this is some sort of correlation factor, as you may know, we're looking for this to prove that we've got a background of gravitational waves that's statistically isotropic. This is called the Hellions and Downs curve, and it's mostly quadrupolar. When I say mostly quadrupolar, I mean that if I take the shape of this curve and decompose onto Legendre polynomials, then it will have zero monopole. The monopole in this case is a flat line. It will have zero dipole. In this case, it's a cosine, but it will have mostly quadrupole, where the quadrupole will look like this. Okay, so that just means that if I decompose a correlation signature onto Legendre polynomials, the monopole Legendre polynomial is a constant. So that's why when we talk about monopole correlation signatures, it looks like a constant across all separations of the pulsars. It's just a constant offset. If we talk about dipoles, we're talking about something that's cosine in the angular separation of the pulsars. If we talk about quadrupole, we're talking about something that's cosine squared in the angular separation of the pulsars. So it's a good question. It's just different terminology. So whenever we're talking about stochastic backgrounds and we talk about monopole, dipole, quadrupole, we're almost entirely talking about shapes in the correlation pattern. When we're talking about the amplitude of gravitational waves, other things like that, we're probably talking about moments of the matter distribution, monopole, dipole, quadrupole moments. So it's a difference between moments and shapes, essentially. Does that help?
Yes, thanks.
Any other questions in the room? Yeah.
So gravitational waves are kind of unique in like the wave family of waves. Because they don't, do they disperse or?
They can actually, under certain circumstances, you could imagine, you can get lensing of gravitational waves, and you can bend gravitational waves. So you get a form of refraction, maybe if you can arrange black holes in a certain way. We don't have that technology. So it's a lot of the wave characteristics that you associate with other types of waves can be made to hold for gravitational waves too. People are really interested in lensing signatures of gravitational waves. In fact, I'm not sure what the current thinking is, but there were some papers out in the early years of LIGO claiming that the black holes that were being observed were actually lensed events from much farther away. I think the weight of evidence is now against that, but it was a theory at one point. So you can get lensing. Yeah.
Can you explain why the emission of gravitational waves is binary systems from really sensor formats to?
Yeah, it's a great question. So I'm just going to do it sort of in a cartoon sort of drawing way, but I think it's helpful. Okay, so imagine we start out with, let's imagine we've got, this is total mass in the system. This is the reduced mass in the system. And so the total mass occupies one focus of the ellipse. So we've just got our reduced mass orbiting around like this. Now the amplitude of gravitational waves is larger when the system is close together. So something that's tight together and is orbiting will generate large amplitude gravitational waves. So whenever this reduced mass comes over here and is emitting gravitational waves, it will emit a large amplitude burst of gravitational waves. It's a continuous process. It's always emitting gravitational waves, but you get kind of an intuitive feel if you imagine that when it's close here, you get this big burst of gravitational waves. And that leaks energy away from the orbit. So it doesn't have enough energy to stay bound and still move over here to the farthest extent, which is apogee. So it goes over here instead and comes back. And it will keep emitting gravitational waves until eventually it sort of circularizes. So it's mostly because you've got this asymmetric energy flux, big flux when the system is close together, not very big when the system is far apart. But instantaneously, if you've got the emission of gravitational waves when the system is close together here, then the system has to stay as it is. Like it's not as if when you emit gravitational waves, suddenly the reduced mass of the system moves inwards like a delta function. It still moves. And so that's why kind of does this. And you get this circularization. So it's that the system is no longer able to get out to the apogee that it had before. And it just becomes closer and closer that it's able to get away from the total mass until it eventually circularizes. All right.
That was going to this exact question. When you release gravitational waves, we know that you also in this model where we're assuming something energy with a bit is essentially like over it or
yeah, I mean you're right, it's losing the total energy in the orbit is changing. I would consider in point masses, but where you would really see changes in the mass of the objects, I think would be very, very close to merger. So we don't really consider them as losing mass before they've coalesced. It's they're 30 solar mass, 30 solar mass. And when they're far enough apart that the equations I talked about still apply, you can just treat like the Newtonian orbit. But when you're in the last handful, maybe 10 cycles before merger, that's when you have to get into something called post-Newtonian corrections. And you have to consider higher order terms. It's no longer nice linearized GR anymore. It gets into the regime where you need higher order corrections. And then eventually, in order to make it merge, you need numerical relativity. So it stops becoming something that looks like 2-point masses. When the black holes actually merge, it's more like 2 water droplets deforming. Like the event horizon, the ergosphere, the other kind of causal properties of the black holes start to deform and then kind of fuse together until eventually you get this wobbling thing at the end, which eventually settles down.
There's no symbol form of TNT.
I don't think so. There are numerical prescriptions that people have worked out that relate the total mass before merger to the final mass of the black hole, also as a function of spin as well. So you can write those things down. It's just, I can't think of anything off the top of my head that's analytic. Yes.
Really, the first cycle it takes to become circularized to the Earth masses.
Yes, I mean, so the eccentricity is a continuous variable between 0 and 1. And so it depends what you mean by circular. It could be infinitesimally, like an eccentricity of 10 to the minus 5. So if you establish some sort of threshold and say, our detector doesn't know the difference between 10 to the minus 5 and 0. So by the time it gets to 10 to the minus 5, it's circularized. If you say that as a threshold, then absolutely you can work out the number of cycles it would take to circularize in terms of the chirp mass of the system. Now, we haven't talked about chirp mass yet, but the chirp mass is just a convenient combination of component masses in a binary system that we use often in gravitational waves. I'm going to be brave and pretend that I can, off the top of my head, write this down. I think it is something like M1, M2 to the 3/5 over M1 plus M2 to the 1/5. So M1 and M2 are just the component masses in the system. The reason why we use the chirp mass, all the equations involve quantities that have something like this. And so it's just very convenient for us to talk about the chirp mass. Yeah.
Just that gravitational waves carry away. I'm not sure if this is a fair question yet, but if you have a higher order, like you don't do linear gravity, you get some sort of coupling between different gravitational waves. I guess perturbations cause other perturbations.
Yes, you can. So let me answer that. And there are 2 parts of that. You can get gravitational waves superposing and constructively and destructively interfering. Can't get that. And we'll see a part of constructive and destructive interference on Wednesday when we start talking about stochastic backgrounds, where gravitational waves from all over the sky are adding up together. Another part of that is that you can actually have gravitational waves being emitted from a small body in the system, reflecting off the central black hole and the central compact object, and I think sourcing further gravitational waves. So you can have like a back reaction where the emission of gravitational waves can actually generate more gravitational waves. It's non-linear, and it's certainly not just additive. So it's not as if things blow up to infinity that you just get this endless feedback cycle. It dies off. But I believe that can happen, yeah. And if we take into account things for what LISA, which is going to be a space-based interferometer in the 2030s, what LISA will be able to measure, then LISA might be able to measure effects of higher order sourcing of terms like that. Yes.
I think the mass ratio of our system affects the gravitational wave, including like how we do that in our solution. We're looking at systems that have the same mass.
Right. Good question. So that's where, when we consider unequal components, that's where the chirp mass becomes useful, because we can deal with just the chirp mass in terms of the component masses. We can just trivially rewrite this in terms of the mass ratio and the total mass. If you keep the total mass fixed in the system, but you dial up or dial down the mass ratio, then at low values of the mass ratio, the amplitude of gravitational waves is proportional to the mass ratio itself when Q is small. Generally speaking, if you decrease the mass ratio, so if you make one component much smaller than another, that will reduce the amplitude of gravitational waves. You get the biggest impact, the biggest amplitude gravitational waves when the components are comparable. If there's nothing else, I think we can pause. We can take a break, get some coffee, water, go to the restroom, whatever, and then allow Professor Jani to set up for the next lecture. Thanks so much, everyone. Hope this was useful. Yeah, you can get started at any time. Okay. Expand or contract as much as you can.
Okay, our target is to end by
Target is 12:30.
12:30. Okay. All right. All right, shall we get started? Well, thank you first of all for Professor Taylor for inviting, and it's very nice to meet all of you. I will get a chance to have a conversation with you during your visit to Vanderbilt, which I hope has been great. This is also a very stunning room. This is the first time I'm here in this giving a lecture, so really looking forward. The lecture that I've prepared is a very high level summary of what the 100 years of our field are, of which I would say 50 years in past and 50 years in future, all of that sort of combined into, where the field is sort of moving towards. I'll try to go through some history of why it took so long for us to measure gravitational waves to begin with, what we are doing right now in this decade, and how we are planning things in the future. So hopefully, this is something that sort of motivates you towards being in this field in the long run. We heard from Professor Taylor's lecture about the colliding black holes. How the sources of black holes emit gravitational waves, which releases the energy, the linear momentum, and the angular momentum away from the system. All of that is released as gravitational waves. The collision itself of two black holes is the most energetic event that we know in the universe since the Big Bang. And almost 95% of the entire energy is released at the point of contact when the two black holes have pretty much collided, right? There is no easy analogy to sort of comprehend how much gravitational wave energy is released. It is just this billion trillions of times of whatever we can think as a best measurement on Earth as a sort of a catastrophic event like a nuclear bomb can be. But the puzzle here is that even if the collision of black holes emits so much energy, there has been absolutely no way that we as a civilization had access to any of this information much until like less than 10 years ago, right? Until then, we absolutely had no way to know what kind of sources really measure gravitational waves. And the being that the entire energy here has no representation in the electromagnetic spectrum. If you just have two black holes in complete isolation, which is a vacuum solution in general relativity, there is no matter imprint. You can point the best telescopes here when the two black holes are about to collide, and you'll still not see anything that is coming out from the system. Versus when you look at the same image in the gravitational wave spectrum, sorry, the video is a little dark. You can see when the two black holes are coming closer, it is systematically emitting what we call the ripples in the fabric of space-time, which is just perturbations that are taking place. And over the time, these waves travel the entire observable universe without getting distorted, without getting the information lost from the time where it was emitted. Every particle in the universe gets to hear about any gravitational waves that is emitted. Right, so this is the most fundamental way that the universe actually communicates with us and with itself, right? Because everyone here gets to hear about the incoming gravitational waves. Now, the way the gravitational waves interact with us is a bit counterintuitive compared to how light interacts with us, because light travels on the space-time, while gravitational waves is the stretch in the space-time. This is just an image of a highly sort of exaggerated image of gravitational waves passing from Earth temporarily would stretch the entire Earth, and you can see that the stretch in frequency when it is happening is based on the frequency of the incoming gravitational waves. Of course, this is extremely exaggerated. This does not happen. Otherwise, we will have ocean waves coming out of directly gravitational waves, right? Which doesn't take place. But this possesses a challenge of what we mean by measurement of gravitational waves. Because if you take a ruler and have, you and your friend are separated by a distance and you're trying to measure how much was the stretch because of an incoming gravitational waves, the ruler itself stretches because the entire space has stretched. So how do you make a measurement when every reference point around you is impacted by the gravitational waves? And this is really where the start of the field happens, that even though we knew gravitational waves exist, let's say if you just had a cylinder, there is a very particular way that the polarization of gravitational wave would stretch the cylinder, but the effect is so minuscule that, at least in the lifetime of Einstein, he thought this is completely not an observable phenomenon. Though the more serious attempt to measure gravitational waves had actually started in the 60s. So I've divided the lecture in like 4 major themes here. The past of gravitational wave detectors in sense of what can we learn from the attempts that took place in the last millennia to measure gravitational waves. What is the current present of gravitational wave, which is practically since 2000 to now. The future, which is roughly the 2030s era of the gravitational wave detectors. And I'll call more distant future. I'm afraid to put any numbers of the timeline here, because every project in this field has been generational. Like, as we'll speak about, projects like LIGO, LISA has been there, for a good of half a century in the time frame, right? It takes that long to realize an experiment. An image as a comparison here. I asked DALI to give me an image of gravitational wave observatory. It gave me an image, and I don't know what it is. So that's just where the state of the art is. Let's start with the bar detector idea. So this was in the 1960s, and Joseph Weber, who was a professor at the University of Maryland, had this very ingenious idea that if you had a large bar made up of aluminum or silicon, and if you have this incoming gravitational waves that stretches the space-time, you could, in principle, if you were to measure how much the stretch of the cylinder is, even at a very atomic level, if the incoming waves are in resonance with bar, you would be able to measure this kind of a system. And in the process, he devised a lot of the foundational data analysis techniques that we use in measuring gravitational waves today. That how can you be certain that this is a gravitational waves coming from something which is cosmic and not just from a terrestrial impact that would change the bar detector itself. So this is an image of him with the bar detector, which was placed in the University of Maryland, in the basement, I believe, in the University of Maryland. And then in 1969, he made a claim that the bar detectors measured gravitational waves from a cosmic event. And actually, if you see the paper, he has done the sophisticated data analysis the way we still do in LIGO, we still do in, let's say, pulsar timing, to ask what is the background noise versus what is the significance of this being a real event. And there are 2 bar detectors. There was one in Illinois at the Argonne National Lab, and the other one was in Maryland. Both had a separation of about 1,000 kilometers. And this is the coincident mark that he felt that the true gravitational wave has been seen. After this announcement, several gravitational wave detectors, much more sophisticated in nature than the ones that Weber had, were built in CERN, were built in Italy. There was one in Louisiana here. There was one at Leiden University in Netherlands. And none of them ever measured any signal like this. Now, the trick with gravitational wave detection is that the universe is constantly humming. So if you see it once, you will see something in the vast universe again. Right? This is not a one-off phenomenon that emission of gravitational waves from astrophysical sources is. So much so was the convincing, I would say, nature of Weber that in 1972, when the last set of astronauts ever stepped on the moon, which is an Apollo 17 mission, one of the experiments that they took to the moon was a gravitational wave detector that Weber had built. And the idea Weber had was that not just that, your small bar detector you have on Earth gets into resonance, but then the rest of the Earth itself is humming, so it's very hard to isolate the two. But if the entire moon gets into resonance with gravitational waves, you would be able to hear or separate some sort of a humming that the moon takes place. You can think of the moon as a rigid body, which the incoming gravitational wave is literally like stretching and shrinking. And so you had an experiment there, and I like this opening lines of the paper, and the description of this experiment was the primary objective is to use moon as a instrumental antenna to detect gravitational waves created by Einstein's general theory of relativity. Gravitational waves carry energy, momentum, and information concerning changes in the configuration of their sources. So pretty spectacular. This is an actual image. Now, sadly, the detector did not work, not because the foundational idea of Weber was already flawed, but also there was a manufacturing defect while taking the experiment up to the moon. It still worked as a great seismometers, which led to a lot of seismic studies, which was the secondary objective, actually, or one of the objectives in this experiment. 1980s, there were indirect evidence of gravitational waves. So there was this very famous Hurley binary pulsar, and several years to decades of measurement of the pulsar led to an understanding of how much the periastron shift happened within the binary over the time. It matched exactly with the prediction of general theory of relativity. So this was a very, very compelling case that yes, gravitational waves A exist in the universe, and B, they are very similar to the prediction of general theory of relativity. It does not differ, at least in the level at which the binary pulsars were being measured. So this is the line from the press release that the Nobel Committee had, that the good agreement between observed value and the theoretical calculated value of the orbital path can be seen as an indirect proof of gravitational waves. We will probably have to wait until the next century for a direct measurement of gravitational waves. This was a 1993 Nobel Prize. Now, this is where the real semantics comes in. We knew indirectly that gravitational waves exist, very strong. You can make almost like a 5 sigma equivalent with the Hurley binary. However, that is still not equal to saying that you have detected gravitational waves, because a detection refers to a direct measurement, not an observed phenomenon. In this context, dark matter is an observed phenomenon. We know the universe has dark matter, but we have never directly detected dark matter. And this is the same subtle difference that was there in the case of gravitational waves. Now, but because already, the mounting influence that Weber had, this is a very nice quote from one of the founding, one of the leaders of the LIGO collaboration that eventually detected gravitational waves. It said that Weber lived long and active life until 2000. He never agreed that his results were wrong. The one time that argon detector and the one in Maryland detected gravitational waves. He kept making observations and announcing detection. So he also thought that he had seen the famous supernova that happened within the Milky Way, the 1987 supernova. And his continual presence reminded us that our field was born in controversy. Without any formal closure, it was hard to leave that episode in past. In effect, we replayed the Weber affair all the time. And this is something which became a bit controversial on the sense that can we ever make a direct measurement of gravitational waves that would convince the larger scientific collaboration world that yes, this is truly a detection. And this came out, and there was another episode, Professor Tira and I were not there when the Weber era was there, but we were very much present when another false claim of a direct evidence of gravitational waves occurred in 2014, when a team, which is the BIPER, which stands for very nice acronym, I like it. It stands for Background Imaging of Cosmic Extragalactic Polarization. It's an experiment in the South Pole. They made a claim of discovering gravitational waves in the very cosmic microwave background. So the universe, when it would have started, the space-time was the first thing that was created. So there has to be some ripples that in the fundamental space-time of the universe. And that was the claim of a measurement of it. It was in March 2014, they announced, and this is a press release, that the first direct evidence. And then January 2015 was this article from Nature that the gravitational wave discovery is officially dead. Right, so this is even in the modern era where we have all the other sort of, known scientific techniques, still was challenging to measure gravitational waves as a direct evidence. So the concept that really worked and is at the foundation of today's gravitational wave astronomy is the concept of laser interferometer, where you can say that, yes, a direct imprint on the matter is very hard to measure. However, if you do have a laser bouncing around an interferometric setup like a Michelson interferometer, then the change in path length from the gravitational waves would make one, if the default setup of the experiment is a dark fringe, you would start seeing, bright fringe because the path length have changed. So this was actually an unpublished study. This was a lab report, internal lab report at MIT, where Rainer Weiss, who later on went to win the Nobel Prize in Physics in 2017, devised this idea that you can, in principle, measure gravitational waves. Right? This is, let's see if this animation is up. So the broad concept would be that, well, it's still pretty difficult to do a lab experiment like the bar detectors who are lab size experiments to measure gravitational waves. But if you have the arm length of several kilometers in which the light is bouncing around, for several hundred times, collecting, much solid inference of the path length. And then if you have an incoming gravitational waves, it will change the position of the mirror. And that tiny fluctuation is something that you could measure because you're not directly measuring the change in path length. You're measuring what is happening to the interferometric pattern. So if you have a gravitational wave coming in to a laser interferometric detector, it stretches one arm, but it will not stretch both the arms in the same way. So it stretches one arm slightly more than the other. In that case, you would see the change in path length that results in a bright fringe being a dark fringe. And you could record it as a function of time. And that is an equivalent of noticing photons in your electromagnetic telescope. So if you build an X-ray detector, if you build a gamma ray detector, you collect the number of photons, and that's how you know that you're seeing an actual observation. Equivalent to that is seeing the change in path length on the gravitational wave detector. So the experiment then eventually that formed it is called LIGO, which is the Laser Interferometer Gravitational Wave Observatory. It started construction in 1990. It's operating since the year 2000. It has been, several hundreds of people have been involved with making this experiment a reality. During my graduate school days, I was stationed at this very facility, which is the LIGO detector in Livingston. The arm length of how much the laser travels from the point of where, it starts at the center, it's 4 kilometers, it's 4 kilometer and 4 kilometer exact. And there are two such LIGO detectors. One is in Louisiana, which is where most of my students in my lab end up being fellows at. And then another one is in Hanford, which is in Washington State. And since the construction of the two LIGO, which actually has a separation of about 3,000 kilometers, there is another detector that was built in Italy, in Virgo, which is a spectacularly nice site. I love the US detectors too, but the one in Italy is really nicely located. And there is one in Kagra, which is inside a mountain. It's inside where the neutrino facility is. It's called Kagra. So these are the 4 active gravitational wave detectors running right now as we speak. So these are all four active. We're looking at gravitational waves. And there is another gravitational wave detector, exact replica of the two LIGO detectors in the US, is going to be built in India sometime by early 2030. So that forms what we call the current Earth-based gravitational wave network. Now, the sensitivity of the change in path length that you're trying to measure of incoming gravitational waves is really your sort of money plot, right? How good can you measure the incoming gravitational waves? So we use this a terminology called strain. This is a strain which essentially means the change in path length over the total distance. So it's a dl over L, it's a dimensionless quantity. The plot, you will see this across gravitational wave detectors. This is how we define how well can we see a certain phenomena in the universe. So the y-axis is the strain that goes across several orders of magnitude, like in this case from 10 to the power minus 15 to 10 to the power minus 24. And then the x-axis is the frequency within which you can detect gravitational waves. So these are the only frequencies of gravitational waves you can see. Not every frequency that exists, but very specifically within that window. It is same as saying, if you have a telescope, which is a visible light telescope, you're not going to see any radio events. It's only within the visible spectrum that you see gravitational waves, right? So the change in path length, if you want to really compare, so this is the diameter of a proton is about 10 to the power minus 15 meters, right? That is our absolute atomic level accuracy of measure. The incoming gravitational wave detectors, at least the sensitivity of LIGO, when it started in the year 2000, till when it stopped operating in the year 2010, which is the initial LIGO era, reached about 10 to the power minus 21, which is 1/1,000,000th the diameter of a proton to measure the gravitational wave change. Right? This is the accuracy that was already there in the year 2010. And we had not measured any gravitational wave events up to actually this point. Then in the next avatar of the experiment, which is still the same facility, it's the same 4-kilometer facility, everything by and large remains the same, except there are fundamental changes. For example, the isolation system, the seismic, how much the mirrors are separated from any activities around, whether caused by environment or caused by human activities, can it be separated? And over the time, right now, LIGO has about a peak sensitivity of around 10 to the power minus 23, which is 100,000,000th the diameter of a proton. Right? There is nothing equivalent of this ever done in any branch of science in terms of measurement accuracy requirements. So finally, in the year in 2015, on September 14, which was also a Monday, the computer, it's about 461 Mondays before today, when some of us were fortunate to see this gravitational wave event, which is we use the telephone number. So the GW is the tag, and then it is year, month, and date, which confuses some part of the world because it should be year, date, month, or month, whichever. But it's 1509-14 means September 2015. September 5th, 14 on 2015 is the day that we saw the event. Now, the event that you see in gravitational waves is not really clear that it comes from a binary black hole, right? Because the detector only measures the fact that it is stretching as a function of time. And then two detectors are simultaneously stretching. That is a requirement for claiming a detection that two independent places should measure gravitational waves, because otherwise it's very hard to have your confidence that yes, this is actually an event. So what you see in the frequency versus time is what we call a spectrogram, that there is this burst of energy that is happening at around a few 120 hertz. And then it's increasing as a function of time. So the frequency is increasing as a function of time, which we call the signature chirp. You can fit the F dot here, and that directly relates to chirp mass. That tells us what is the mass of the binary if this has created gravitational waves. And then you can draw this in a wavelet domain. So you can make a waveform which has a function of time and amplitude. Now you see this pattern, the gray is what the observation is, the yellow line, very thin, sorry to see in this plots here, is the prediction of Einstein's general theory of relativity that matches with the incoming waves. And if you try to make a full 3D simulation of the gravitational waves matching Einstein's equation, which is called numerical relativity, in there you can see that once the black holes are coming closer, the space and time is releasing these ripples. And in the line of sight, if you draw a trace, it becomes, instead of a three-dimensional phenomenon, it has this 1D trace, which is what we called the gravitational wave morphology that we have seen, right? We don't see the whole 3D phenomena like you would see nicely with a radio detector or an X-ray detector. You can make a 3D map of the Crab Nebula or something. In gravitational wave, you only see a one-dimensional trace line here. Since 2015 to present, we have seen about 200 gravitational wave events. These are public alerts, of which 90 are confirmed gravitational wave events, that there is no doubt. And after the fourth observing round, there is, we send out online alerts. And by this time, if we don't retract any signal, that really means that this is a true gravitational wave event. There's a nice plot, infographic, that if you go to the list on Wikipedia, list of confirmed gravitational wave events, the y-axis here is the solar mass. And there are three solar masses here, right? One is, your primary mass of a binary, the secondary mass, and both collided to form a final object. There are three things each event gives. The x-axis is your distance, how far from Earth has this phenomenon, this waves have come from, which is same as saying the age of the universe. Like you can see how the farther from the signal it comes, you can measure directly the age of the universe. So every dot here refers to a black hole or a neutron star that has been observed over the last, I would say about 9 years, right? Since the first gravitational detection. You can also see the interesting things are there are these gaps where we were not expecting any objects to be there. For example, we know after a certain point, you cannot make a neutron star. It's just not a stable solution. And then there is another point after which only black holes start forming, but you can't keep making very big black holes because big stars don't exist that often. And those kind of gaps have already been filled with events. So there does exist some sort of an underlying phenomena that the universe uses to make black holes that is not very straightforward or conventional from the evolutionary stellar perspective. The farthest gravitational waves that we have seen have been at least halfway across the total age of the universe, right? So this is redshift 1, which is about 6 giga years away from where, or the age of the universe was about 6 giga years. And since the fourth observing run, we have started seeing even farther and farther in the universe. So a question that always gets asked is, you have the same experiment, and nothing much has changed. You have made, changes, but it's not like you have completely made a 4-kilometer experiment into a 40-kilometer experiment. Now, how come you now detect gravitational waves and you could not do it for the first 10 years? And it really has to do with what creates gravitational waves that we are trying to measure. Initial LIGO was perfectly capable of detecting gravitational waves if they happened close by from. There was nothing wrong in the technique of measuring. It's just that the sources are so extremely, extremely rare that we have to span a huge survey of the universe to get a handful of confirmed detections. If you increase the volume, the sensitivity that we were looking at, the strain as a function of frequency, if you can see the strain at least an order of magnitude further down, the volume that you're looking at increases by a factor of 1,000. So here is a comparison of how the volume that initial LIGO was able to see versus the volume that advanced LIGO, which is since 2015, is able to see. And you just see the scale, and this is a map of all the known clusters in the local volume, slightly above much above the local volume. You can just see the sphere at which advanced LIGO can see. And this is only for binary neutron stars. The binary black holes, you can see so far that there is no map, that we can compare against. The estimate that we have, observed estimate, that how many collision of stellar black holes happen is about 10 per cubic gigaparsec per year. That's the units in which we define. So cubic gigaparsec is the volume that if you can see. So cubic gigaparsec refers to about 3 billion light years in distance. And sorry, a gigaparsec refers to 3 billion light years, and then cubic gigaparsec is the volume enclosed per year. Like how many collisions are happening per year? If you convert this, that means there are about 1 binary black hole merger has taken place in Milky Way in 1 billion years. So if initial LIGO would have waited 1 billion years, we would have definitely seen a gravitational wave event. But the point being, how much in this sort of human lifetime can we see this event? And to remove our luck, we just have to observe farther and farther in the universe. To get a sense of how rare the collision of black holes is, there are about 100 million to billion stellar black holes within the Milky Way. And half of them are in binaries. But they have to be so close to each other, the distance between the black holes has to be less than the distance between Sun and Mercury to see a measurement of gravitational wave within the Hubble lifetime, within the age of the universe. So you have to bring them extremely, extremely close, which is a very rare chance. And that's why we don't see millions of gravitational waves coming by, but we only see tens coming by. Any questions so far? All right, so LIGO is working fantastic. We are seeing hundreds of gravitational wave events, which each event is unique, and there is a lot of astrophysics we can uncover from every observation, and a lot more with the bulk measurements. But there is still so much in the universe that LIGO cannot see. So quick exercise, in the interest of time, I will sort of go ahead and just give the answers here. This is a formula you can use to estimate the gravitational wave released right in the last circular orbit, before which, it's essentially going for the merger. So it's the innermost gravitational wave, the gravitational wave from ISCO. And it scales inversely as a function of total mass of the binary. Right, so in this case, if you put 2 neutron stars, which is about 1.4 plus 1.4 solar mass, you see that the last stable orbit is around 800 hertz. And that is the closest, after it goes. The same for a stellar black hole like the one that LIGO discovered comes to around 30 hertz. Again, this is the last stable orbit. After that, it still has to go through merger, it still has to go through ring down. So that is always much higher frequencies. But this is the frequency at which you can keep the orbit stable, after which, it becomes a point of no return. So the window that LIGO can see in the characteristic strain plots that we saw is from 10 hertz to a few kilohertz. That is all that you can detect gravitational waves with a detector on Earth. So if you took a Milky Way galaxy and collided with another Milky Way, so you have these 2 supermassive black holes that are trying to collide with each other, which again happens because we know colliding galaxies is a phenomena that is happening in the universe across its evolution. The waves would be of the frequency of around 0.2 millihertz. You cannot detect that with LIGO. If you took M87, the very famous image of the black hole that the Event Horizon team had, if there was about 6 billion solar mass black hole, if you took 2 of those and collided, it would be at around hundreds of nanohertz. So again, that cannot be seen by ground-based detectors. This brings to the point that LIGO alone is not enough of a gravitational wave detector. We have a much larger spectrum in which different sources of astrophysical interest exist, and we need each of those sources to be measured for different motivated studies. If you are interested in the growth of the universe, you need to know how galaxies form. And that means you need to know how the supermassive black holes at the centers of the galaxies form. That can happen partly with a space-based detector that is coming in the future. And so with the pulsar timing array, which is at nanohertz that is being currently observed already. If you see in the scale here, right now, the only experiment, the first experiment we had was the LIGO, which is a very high frequency event. So the way I like to think about LIGO is that you first made an X-ray telescope, right, which is equivalent to that. Then there is a space-based mission that is coming, which is LISA, which is, you can think of that as an infrared telescope. Then you have nanograv and the pulsar timing array community, which is more as it uses radio, and the analogy fits, it's a radio equivalent wave. It's a very low frequency. And then you have cosmic microwave background, which is the imprint of the earliest gravitational wave that the universe released, which may or may not be fine. That is a much, much farther goal than the rest of the astronomy community. So LISA, that would open the millihertz regime of gravitational wave. It is the most ambitious space-based mission ever to be built. We will get more information from Professor Taylor now that he's in the LISA science team about the technology behind this process. We can think of the scale is the Earth-Sun separation length. The LISA LIGO is separated by 4 kilometers. LISA is separated by 2.5 million kilometers. And then the fact that you have such a huge base length allows you to find wavelength of the size of the detector, right? If a 1 million kilometer wavelength source would come to Earth, it would really just pass through it. We would not have a measurement. So to make a measurement, you have to have an experiment that big. Right? We do know that the fundamental technologies that would make the LISA project works because of Pathfinder that was put at the Lagrangian point 1, which tested that, yes, exactly, you could make a measurement of gravitational waves in the space, in deep space, although this is still in the mid-2030s, right? This is at least 10 years in the future when this project will be launched. Another next generation LIGO-like gravitational wave detector on Earth, now that we know LIGO works. So it makes absolute sense that we wanna go to a new infrastructural facility. So we can discover, there are things that you cannot do changes in LIGO anymore because you're limited by its length and the building sizes. So there are two concepts, both being advanced at respective origins. So the Cosmic Explorer is the top priority project from the United States. It will make a 40 kilometer by 40 kilometer line. 40 kilometers is so far that the curvature of the Earth comes into play. So you have to dig tunnels just to have your beam length being straight. This is scale. If you want to think about, should have a map of how far from here 40 kilometers. I think it's possibly something like Mount Juliet or more. The other concept is Einstein Telescope, which is the flagship project from Europe community, which tries to build a gravitational wave detector underground, just like how the sun or the Large Hadron Collider is underground. It will be a 10-kilometer triangular facility that will be measuring gravitational waves. It's inside, it doesn't look so much, but these are multi-floor tower length that you have to dig to make the seismic isolation really work out the way you want to have a significant improvement from where we are currently making gravitational wave measurements.
Since the Netherlands and Sardinia are bidding to have the site in their applications, which is this landscape meant to be?
Oh,
is this the Dutch coast or is this Sardinia?
It does feel like this is the Italian coast.
Yeah.
But there is a third contender of Germany too. It's the morphology of the experiment, whether a triangle or L, is now still under discussion because the triangle, drilling is very hard. And especially when you have to do this 40, 50 kilometer underground tunnels. And that is just the beam length. You still need a lot more space around hosting the experiment. So it's still being worked out whether a triangle or an L shape is a more optimal design. But just to tell you as a reference point, LIGO India is an exact replica of LIGO, and it still takes about 10 to 15 years to build it. Just the civil infrastructure of a 4 kilometer by 4 kilometer interferometer. So if you see a concept like this is definitely not happening in a graduate school lifetime. This is a several decades of development. Now, the result of it is such a substantial improvement that it is definitely worth a multi-decade, and these are multi-billion-dollar missions that will take to realize this. So in the same strain plot, the strain versus frequency, LIGO during its third observing, which was in 2020, compared to that versus what is promised to achieve with Cosmic Explorer, is 100x improvement in the sensitivity measurement. So this will still take, just like initial LIGO or advanced LIGO did not reach its design sensitivity the day you start operating. It takes almost a decade of calibration to really know the sources of noise. To achieve this sensitivity, you're looking at late 2040s or early 2050s in a very realistic sense. How long does it take? But the fact that even from the start, it would already be a substantial improvement in what we have present with LIGO builder. Right? The thing though here is that even if we are making this experiment, it is not changing the frequency window of what you're observing. It is still within around a few hertz, with the peak around, the better sensitivity around 10 hertz to a close to a few thousand hertz, which is what you already have functioning with LIGO Virgo Kagra. It's simply, you can think of it, you can think of this as the equivalent of Hubble being made later on into, much powerful like James Webb Space, provided it's looking in the same frequency spectrum. Well, it's the same effect. If you have a detector so sensitive as Cosmic Explorer and Einstein Telescope, the number of gravitational wave events you can see is just unprecedented. Here is a plot from 2015 to, let's say we can start first comparing to 2024 right now, where the fourth observing run is going on. Each O refers to the observing run. So O1 is the 2015 to 2016, O2 was 2017, O3 was 2019 to 2020, and O4 is right now started in 2023, and it's ongoing. In each of the y-axis being the number of directions, so in each of these observing run, the number of events have sort of, logarithmically increased. We went from 3 events in O1 to right now having 200 events in fourth observing run. We will have the fifth observing run later by end of this decade. You will have a cumulative catalog of confirmed gravitational wave events of about thousands for binary black holes. And for neutron star, you will have at least about hundreds by end of this decade. Then there will be improvements to the existing LIGO facility, which will work as a pathfinder or a technology demonstration for future detectors. Project is called A-Sharp, so it is still your existing 4 kilometer LIGO. We are going to make some changes that can be as a test. In that duration, you will reach in those eras of mid to 2030 to mid 2030s, you would have at least 10,000 binary black hole individual events detected, and the neutron star would be in the range of thousands. And as soon as you have a Cosmic Explorer or Einstein Telescope, you will have hundreds of thousands of detections every year. Your cumulative total events you would have seen would be million by end of 2040. Right? This is equivalent of the large surveys like LSST and others promise of the galaxy distribution. This is the same that we are doing with gravitational waves. The reference point here, however, is the collision of two objects and not the spectrogram of a galaxy or an AGN or something, which is what electromagnetic community uses. It. The different equivalent we have. But the argument is every binary black hole or a binary neutron star is not existing in thin vacuum. They must have an underlying galaxy or globular cluster or some environment. You can use that as a reference point that this is a matter. You're really probing the large scale structure of the universe. So when you combine all the detectors, that would see merging binaries. It does not include the PTAs here in this plot. But if you include all the merger events, that would be stellar black holes for LIGO that we see right now, then the Einstein telescope, Cosmic Explorer. And then you add LISA, everything that LISA would also see, which would be mergers of supermassive black holes. But which kind of supermassive black holes? More Milky Way kind, not the billion solar mass, more like millions or tens of millions solar mass. The x-axis here is the total mass of the binary. The y-axis here is the redshift at which you can see the mergers taking place. The farthest, and this plot is a little aged now compared to the GWST result, but let's say the farthest galaxies or the farthest stars are around redshift of tens or 20. I mean, there is absolutely nothing in the universe after redshift 15 that we have made a confident detection of. An estimated the first stars must have came around redshift of 20 to 30. So everything that the universe has made that has collided since in this mass range of 1 solar mass to about 100 million solar mass will be observed. There is nothing left in terms of trying to understand the colliding black holes. This is very unprecedented in astronomy that you can cover such a wide range, just in a decade of experimental projects. A different way, than the laser interferometry concept of detecting gravitational wave is the pulsar timing array, where you have instead of the biggest baseline you can think of making on Earth is a few million kilometers, because that's how far you can essentially have two satellites that can communicate and keep them in a stable orbit. But if you want to go at a wavelength of parsecs, which is bigger than the size of our solar system, then you have to ask for cosmic events that become your clocks and tell you about a displacement that has taken place, which is the principle of pulsar timing array. So you can have a series of pulsars separated in the nearby in the local volume around our solar system, measure them, and then look for the change in path length, essentially the same way that we do. Here I've taken just a plot from the square kilometer arrays projection. And the way to think about here is that the more the number of years you observe, your sensitivity is continuously improving because of your observation. So between a 5-year to a 30-year observation, you improve by a factor of an order of magnitude. So this is of course, you should start as early and then wait for the data release for getting the best sensitivity estimates of the gravitational wave. In this case, this is a mix of both being a stochastic gravitational wave background, while everything in LIGO, LISA, the sources that I mentioned, are standalone sources. We would also see stochastic background, especially with third generation detectors like Einstein telescope. But that's a slight technique difference here. We see, in this case, you see continuous sources. Also gonna let this go. So this feels like we have enough for the field to mature till 2040s. There is no need to propose anything now because we all have our hands full. We have LIGO, we have Cosmic Explorer, we have pulsar timing, we have LISA covering all the bands. But a lot of these experiments have taken 30, 40 years of concept design, technology development to finally realize. And so the community has now been actively thinking, what is the next gravitational wave detector concept to sort of build around? I'll make this very simple. I'll use the slides. You can use the slides here to have a Python script for this formula. I find this extremely useful to have a quick Python to tell me how long would it take for a binary to merge. So if you start with a binary neutron star, and you start at the lowest frequency that LIGO or Cosmic Explorer can measure them, then the total time before it is going to collide is about 15 minutes. And that's all that you have really measured the gravitational waves. You have measured for 15 minutes and then the merger happens. If you had LISA 0.1 Hertz to measure this gravitational wave from neutron star, which you would actually miss it because the amplitude is not big enough for LISA to see, you would have seen it at least 6 years in advance, the very same binary, if you had a 0.1 Hertz measurement. And if you had it at around 1 Hertz, which cannot be seen by neither LIGO nor LISA, you would have still had a 5 days of heads up. Right, so what can you do with this kind of a heads up? There's a plethora of science. It's just a sort of a plot on saying the characteristic strain of LISA, where we are in LIGO right now in 2024. And there's in between from 0.1 Hertz to 10 Hertz. It's a completely missing band that you cannot make a gravitational wave. If you had an early alert of 5 days for a binary neutron star, you can make the astronomer friends point in that part in sky because you have that kind of an early alert. If you just have a few minutes, it becomes a sort of, you catch it just by chance kind of an event. So this is broadly called the sub-Hertz band, 0.1 Hertz to 10 Hertz. There's not just binary neutron star that you could have, but you could also see the stellar black holes. If you had a detection at around 1 Hertz or 0.1 Hertz, you had several days of heads up that a stellar black hole is about to collide. Then there are black holes that you will absolutely not see with space missions or ground-based, like 1,000 solar mass black hole, that you would start observing in hours to a couple of hours before merger through a detector which could be in between them. Now, why try to find these 1,000 solar mass black holes is because they are possibly some of the earliest seeds that have formed the bigger galaxies. So we want to be able to measure these black holes. They are not coming out of stars, and they are neither at the centers of galaxies. They are really in between, hence called intermediate mass black holes. Several ideas have been proposed over the years on how can we make a sub-Hertz gravitational wave detector. It is fundamentally different than how LIGO operates and how LISA operates, because otherwise you would have been able to improve those detectors and reach the frequencies. But you can't improve LIGO or any ground-based detectors to reach less than 10 Hertz because the Earth is seismically so active that you cannot make a measurement and be confirmed that it's not the Earth that is shaking at low frequency, but an incoming gravitational waves. And the same problem LISA has is that the satellite itself has a residual acceleration because of the short noise of lasers hitting them. And you cannot make a measurement better than what is already. LISA is absolutely state of the art. And to do anywhere better is a much higher difficult technology development. You can roughly classify all the ideas in 4 categories. There is space missions after LISA to be launched in 2050s. You can think about CubeSats being used for measuring gravitational waves. You can have LIGO-like detector on the surface of the moon. And you could also have a completely different technique, which is not laser interferometry, but atom interferometry. For interest of time, I'll skip a lot of this moon things, but it's actually very easy to make a gravitational wave detector on the moon, because unlike on Earth, where you have to build vacuum chambers, the natural vacuum on the moon is already better than the vacuum that is in LIGO facility right now. So it's a natural environment. And this has been known now for several decades that moon is the right place to build a gravitational wave detector. So one concept that we here at Vanderbilt have led and work on is called LILA, which is the laser interferometer lunar antenna. It is you can think of this as a LISA on the surface of the moon, because you have 3 satellites around the crater, each trying to make its own interferometric pattern, just the way LISA does. And we have to do it around the crater because then we can have several tens of kilometers separation without being affected by the moon's curvature. The frequency window that LILA would open is really in between the two, as I mentioned, right? So neither LISA would be able to see that, nor LIGO would be able to see that. It really fits in between band. And once you have a detector in between the two, you can start measuring black holes like 100 to 1,000 solar mass practically across the observable universe. So it's the same plot that I showed with you, but in polar coordinates, where the farthest boundary is the cosmic microwave background, which is the edge of matter formation in our universe. And then you have LISA, Einstein telescope, and Lila seeing different types of black hole masses across a wide range. So for example, LISA would see 1 million solar mass black hole up to like redshifts of 50s to 80s, right? You won't expect any galaxies to be there, but it still has the power to see the universe that far. Same way, Einstein telescope can see tens of solar mass black holes at around the same distance. Lila fills the in-between gap that neither of the detectors can access. Okay. I'll come for the interest of time to the next one. So, well, lunar gravitational wave is only one opportunity. You can still make a LISA-like detector afterwards and try to measure the same frequencies of gravitational wave with a space-based detector. There is a compelling proposal, two compelling proposals. One is being studied for the European Space Agency's Voyage 2050. It's a concept studies on what can be done right after LISA mission is over. And the other is a Japanese-led concept called DESIGO. The DESIGO concept requires 4 LISA to be in orbit around the sun. You can see this triangle. So each triangle, you can think of it as a LISA triangle. There are 4 triangles across the different parts of the Earth's orbit. And then if you just had a LISA like straight up three-link detector, it would require a technology improvement of about 1000x than what is currently already implemented in Lila, or 10,000x, sorry. So 100,000x than what is already implemented in LISA. So this is very, very futuristic. This cannot happen in 2030s or 40s, right? And if you think that this is all that we are thinking about, that's not true. We are also thinking about microhertz gravitational wave detectors. This is the another missing band between pulsar timing astronomy and between LISA. There is a 2 orders of magnitude or more that cannot be seen by any gravitational wave detectors. And there is already compelling science case of why we should be detecting gravitational waves here. These are the sources of 100 million solar mass binaries or 1 billion solar mass binaries, whose merger you want to measure. Because PTAs would measure only that in spiral. Can you measure the mergers? But these are even grander ideas of how do you reach a microhertz sensitivity, which goes 2 orders of magnitude lower than what LISA is operating at. Here you can see actually the LISA curve. This orange bar is really the between what pulsar timing's highest frequency could be and LISA's lowest frequencies could be. And there's just a number of sources being highlighted. Now the concepts are solar system scale. This is the proposed concept on left for the European Space Agency. You see that small triangle, red, in the center, that is LISA, in scale of a microhertz gravitational wave detector. LISA, by the way, is already 2.5 million kilometers. So you are looking at things which are, orbiting different solar system trajectories and trying to do interferometry in between 3 very vastly spaced interplanetary objects. There's another idea that you could have 2 atomic clocks on asteroids in the asteroid belts, because they are very stable and you can use the movement of the asteroids to detect gravitational waves. And there's another idea to measure gravitational waves because the gravitational waves are being constantly emitted, it will get into resonance with objects that are gravitationally bound over its period. So if you have just measured the Earth-Moon separation with high accuracy, it can also detect this microhertz gravitational wave, right? So this is all the future concepts. So in conclusion, we live in this extraordinary time of gravitational wave detection across the spectrum. We already have LIGO, we already have pulsar timing that has had confirmed gravitational wave signatures. So right now, Earth-based LIGO detectors would measure from 10 Hertz to a few kilohertz from hundreds of stellar black holes and neutron stars within this decade. And you would have at least a few hundred events to work around with. PTA will measure stochastic gravitational wave background at nanohertz from potential supermassive black hole binaries with the hope that one of them would stand out from the background. In near future, I would say like near future here is 2030s, LISA will measure gravitational wave from 0.1 millihertz to around 10 millihertz. That's the range it will have its sensitivity, opening a completely new astrophysical window of, that has not been reached by either of LIGO or PTAs. Distant future, I would say, is early 2040s, late 2030s, is next generation Earth-based detectors like Cosmic Explorer and Einstein Telescope. They will still measure between few hertz to a kilohertz, but they would have millions of sources instead of hundreds of sources that we have right now. And then distant square future, this is hard to put a date here, how far it is. There will be projects on the moon, there will be solar system scale experiments that would open the sub-hertz and the microhertz missing bands in gravitational waves. So yeah, I hope that we get to see as many bands that open in our lifetime. Thank you. Questions?
The reason why laser interferometers are not built in the southern hemisphere.
Oh yes, funding. No. So there is a push to have one of the Cosmic Explorer detector in Australia, which will be one of the first southern hemisphere detector. LIGO India is actually going to be the southernmost that we have in the current network that will happen in the 2030s. The incoming gravitational waves, it would be great to have a southern because we have the largest separation. But just within the network, it's not that we are missing out on very big blind spots. The waves are still invisible, right?
When I was in grad school, there was lots of papers are being written about the future network of gravitational wave detectors having LIGO Australia. So at one point it was seriously considered. I'm not sure when it kind of evaporated, but I feel like it was 2014.
Yes. Yeah, and that's when the LIGO India concept took in, because the Australia, the moment that was no longer the southernmost, next option is.
Your waterfall flood is given behind. Yeah, I was wondering, what is the signal to noise ratio needed to make a confident detection with LISA? If you had it.
So here the farthest contour is signal to noise ratio of 8 for an equal mass binary. That is what this plot is trying to show. But then there are these other contours of higher signal to noise ratio. The lowest contour being SNR of 4000. It's an absolute overkill because we'll definitely measure a gravitational wave. It's just the science that we want to get out of it.
There's a question on Zoom.
Please go ahead, Tyler. Do I have to unmute here?
Tyler,
Can you hear me? At the beginning, you mentioned the sensitivity of LIGO in terms of volume of the universe probed. Now that there's an estimate, or now that there's a measurement for the gravitational wave background, is there an equivalent estimate for the volume of the universe probed for continuous waves by pulsar timing arrays?
Yes.
Steve says yes.
It's well, other people here know this as well. It's a few hundred megaparsecs for a billion solar mass, and it's a few gigaparsecs for 10 to the 10 solar mass. Now that's a statement about our current horizon that if anything were nearer than that, we would have found it. It's not necessarily an equivalent statement of like a waterfall plot or anything.
Thanks.
Any other questions for Professor Jani? All right, thank you so much again. Actually, what's the future of CMB-based experiments? Do we know, like, are they working on bicep 3, bicep 4?
So for the Voyage 2050 for ESA, they are considering high redshift mission. So it would be either a CMB or a gravitational wave.
But CMB to try to do primordial gravitation?
Yes.
So both gravitational waves then?
Both are gravitational waves, but I think the case to make is high redshift universe that we observe with gravitational waves. I think by high redshift I mean like dark ages. And what can we learn? Okay.
Well, so practical details, it seems like lunch has arrived. Fantastic, it's from Moe's Southwest Grill, so it's wraps in individual boxes. Please don't take the vegetarian ones if you're not vegetarian. We want to make sure that people are catered for. There might be 1 or 2 that are for allergies or vegan, too. And I think one of them is for William, and William is not here, so we might have some spares. So in terms of, where you can eat right here. You can also go outside as well, I think, and go around the side of the building. There might be seating areas outside if you want to go there. You might go and explore over there. And we've got lots of time for lunch. These extended lunch times are meant to be an opportunity for you to get to know your fellow schoolmates. So go have lunch, explore, and come to me or an organizer if there are any problems. Fantastic.
You can also have some.
Okay, everyone. So this is the portion where we try to get set up for software useful for the rest of the week. The good news is that a lot of pieces of software don't have to be all installed individually. They've been packaged together into Conda installations. So this is the kind of workflow. Hopefully, you've got a working version of something like Anaconda. Anaconda, really, really super useful for installing Python packages and creating a cohesive Python environment. And we'll be making use of Python environments as well. So Python environments, if you haven't really used them before, are specifically designed so that they create like a closed sandbox. So if you create one Python environment that has modules installed in it, then you can do anything within that environment, and then it won't affect things that you install in a separate Python environment. So it's usually very useful to do this if you have separate projects that have different software demands. You want to make sure that anything you're messing around with in one particular environment doesn't affect another one. And environments do that very well in Python. So the kind of workflow here in Anaconda on a Linux machine is you create an environment, a Conda environment called VIPER, and you give it access to Conda Forge, and it's going to be an environment that installs a Python 3.9 environment. Activate it, and then you start installing these particular packages, Enterprise Pulsar and Enterprise Extensions. The good thing about this is that those packages have dependencies, and this will automatically install all the kind of downstream dependencies of these packages. So you probably won't have to do many additional manual installations. The additional manual installations you do need to do are for using Jupyter Notebooks, NB Conda, and then Jupyter Lab. So this is if you actually want to open up something as a Jupyter Notebook in your browser or in something like VS Code, which a lot of us use. The additional thing you need to install is LaForge. LaForge is a really nice post-processing and visualization package created by Jeff Hasbin and his group. And TQDM, which is just like it's like a counter, right? It tells you how far along a job is. What is it?
Progress.
Progress bar, that's the word I'm looking for. What does TQDM stand for? Nobody knows.
Arabic thing.
Is it?
I think, I don't speak Arabic, but I think it means progress.
Oh, I like that. Okay, there you go. So that's the easy. I mean, Linux is the easiest thing. Intel Mac is also easy. Apple Silicon is harder because they make things harder. There are a few additional commands that you need to use, but they're mostly the same as the Linux installation. Some of the PTA software is not yet built to work with Apple Silicon, and so you have to tell it that you're going to install an OS x64 Conda environment, not an OS X ARM64 environment. So that's the first thing that's different. The second thing that's different is that immediately after activating your new environment, you do this line that tells it again, it's going to be an OS x64 environment. That's pretty much it. That's the only thing. So once you do that, this particular environment, even though it's working on Apple Silicon, will be OS X 64 in style. Windows, it's Windows, I don't know. You have to use Windows Subsystem for Linux, WSL. I have minimal experience with that, but we do have people in the room that have more experience with that. So if you have a Windows machine and you've used WSL, probably for scientific programming and installing Conda environments, then maybe this is second nature to you. If it's something you haven't done before, then let us know and we can try to troubleshoot with you. Let's see how far we get through this. Has anybody done this already and had no problems? Oh, awesome. What? Down here? Oh, okay. Interesting.
TQDM is optional. It's not necessary.
Yeah, I guess you don't absolutely need TQDM, but you said 0.6 here didn't install Jupyter Lab? Okay, but you were able to get NB Conda? You were able to get NB Conda yourself through some other way? No. Okay. Okay, LaForge didn't work. That's more problematic. So I think of my group, I have no, you have an M machine as well, don't you? Were you able to install LaForge? Let's see. I'll come over and see what problems you have.
NB Conda is also optional. It's nice to have, but if it doesn't install, we can check why it's not getting it. So, but it's fine. The LaForge is not optional, so that's the only thing.
Yeah.
Take care of.
And if everything worked perfectly, then something else you might like to try is using a development environment like VS Code, which is very, very nice for developing code in. Let me actually show you my environment. Okay, so this is VS Code. VS Code is a full development environment in which you can run things in different environments if you want, different Python environments. You've got a little terminal down here if you want. You can get rid of that. It's got a Jupyter Notebook open. You're running code in this VS Code environment. Also, on the left-hand side, I've integrated it with GitHub Copilot, which is an AI pair programmer trained on all of GitHub code. So if you're having problems trying to debug something, you can ask Copilot if it can suggest a fix. Now, it's not taking the role of you working something out for yourself, but it's like the best version of searching through Stack Overflow you could ever imagine, because it really will be a targeted solution to your problem. GitHub Copilot is free for all students and educators. It just requires you to sign up on GitHub with student credentials. So you can access this if you wish. Another option is just ChatGPT, which is becoming better and better for programming. So given that it seems like most people have actually had success with this, try to help out your colleagues that have not been able to do it so far, that might have had, we all have these idiosyncrasies with our machines where something doesn't quite work. Try to help the person sitting next to you if they're having issues. But we may be able to wrap up this session at 3 and allow us to get on to networking and fun activities later on and finish the day a little bit early as well.
Yeah.
Yeah, you measure these things. I think Kyle, I think if you go to day 2. You can do it. So. When physicists. It doesn't follow the procedure. So I was back. My first job. Oh, I have someone. So. This morning. Because I had to do it. It wasn't very perfect somehow. So you have to individually go. Yes, and there are things that are written. Yeah, you can try and try. There are mappers. There's hard records to see. And again, physicists wrote the. Sometimes you want to fall. Some distributions are like compilers who want the underlying. So you gotta make sure that you're still that software. Still includes. All the This is supposed to be doing, it's a bit either way. This is our company. It was supposed to be a more. But
So if you were tempted by the idea of GitHub Copilot, there are some hoops to jump through. If you'd rather not jump through the hoops, then they do a free 30-day trial. But in order to get it free forever, or for as long as they say forever is, you need to sign up to the GitHub student package or GitHub education package, which will probably require you to upload information about your institutional affiliation and maybe you take a picture of your student ID. But once you do that, once you're registered as a student, then when you try to access GitHub Copilot, the option to have free access will appear to you. So it's not something you're going to be able to do right now. It'll probably require a few days for them to review your ID and actually give you access. But it's a good investment of time. I think it's very useful.
you're right, sure. The enterprise decision. So. Maybe how much you take up? Oh, nice. Oh, yeah. You were like running close. It's not in the action. Yeah. I think we can just take the reading character. Okay, there's not a problem with you, but you architect, you're going to change the issues causes. Because anything selfish, right? You're going to be not going to all the experience in the base team when you go about. There's already else. It's just I don't want you. It's a bunch of wonder versions and versions. I'm not sure if we're getting anything. I think we're right now.
Because I'm trying to, I just. They always, like, you know, everybody's conversation. Well, that's okay. GR. I'm not sure if you can get this, but taking the summit. South Forest is a big area, good research. The idea that. We're trying to fix it. We saw the corrections please from back and very so the back reaction is what this time and our rules have probably but I don't know if you get any more respecting That's a good point. Yeah, starting with you. Yeah. It's good. Yeah. Yeah, yes. I don't yeah, okay. Actually, it should be. Okay. Yeah. Well, I understand. Yeah, so. You guys help this. So. Analysis of like a first community or thinking of what we're doing here.
Can you give that instruction that whole we can assume say. Law court. Don't have anything that needs to be. Because it doesn't have really, or just later.
It's a very good place for kind of launch. Yeah.
Yes, that's the fact.
I'm very
Don't press that card.
Yeah. No, no. Hello. Sorry. Yeah.
It's literally just that first one, you didn't say really cool second. And then you just had it. Because it's already.
Yeah.
Recreate under it.
Well, no, it just remakes that same environment. It'll overrate it.
So, yes.
That's not why.
Oh.
You can do things with this before you do this.
It's like. Yeah. This can be good. I don't know how much experience you have with it.
I need to answer your Slack about the application, but I think I'm supposed to answer, I promise.
Oh, so you were just summarizing it.
Yeah,
Okay. Well, you can
I
just
can-
summary the entire thing.
okay.
Perfect.
I can feel like, is this okay? Cause it asks about like research and outreach, so I was like, I don't like just to separate them. Or I don't know if you want, if that should be more like. in a paragraph.
This,
It just has like.
I think it's for existing contribution. Yeah, I think having it separate is good, but if you can say, you plan to develop this and publish it for next year,
Okay.
just a bit more. prose.
Okay. Or also do that. I never did collaborate with Kim, I think that I met with her. And I worked on my teacher's committee and she told me.
Yeah, I think that's good. And, I mean, the collaboration is planned. We don't have to lock it. So we'll get started on things like networking and introductions by 3 p.m. If you haven't put a slide in already, now's the time to drop it in, and then we can get going. Done? Yeah. All right, so, okay. Anybody else still need some assistance with coding or installation? Well, then why hesitate? Let's just get going with introductions right now. All right, well, today we started in reverse order. We did lectures first, right? And then we're going to introductions. I think a good way to bond with your classmates is to do some hard GR and gravitational waves to get to grips with. But this will help us as well navigate the rest of the week. So I'm going to cycle through the slides that we have. If you haven't put a slide in, like I said, drop one in, got some time, because we're going to go through everyone. We're going to do an exercise that people here at Vanderbilt are very familiar with, called forward. So when your slide comes up, right. Yeah, that'll work. All right, that'll do. When your slide comes up, feel free to elaborate on anything you've written on your slide, particularly if you have pets. Cat, dog, great. And then try to think of what you would say about your family, what your occupation currently is, what your recreation is, and any dreams that you have. So this is a little bit unfair on the first people in the slide deck because they have to think of these things rapidly. So what I'm going to do is I'll do myself first to give people a bit more time. If I can find my slide. Okay. So you can call me Steve. I'm Steve Taylor. I originally from Northern Ireland. Most of my family is still back there. I've got one brother. I have three nieces. Sorry, I have two nieces and one nephew. My parents are still back there as well. And I'm married to Erica, who's up there. That was from a recent vacation we took in Austria. We're hiking around there in the mountains. I'm the butler to Olive. She's here, she's very demanding. She really rules the house. And Erica and I enjoy hiking, I like reading. This is a particularly nice evening that I have recently, making a cocktail and reading a book. And I also like baked goods, so there's that. The two pictures up there are some excitement that I had recently because I had to pass through Venice for a conference. We had a conference for the International Pulsar Timing Array, some of you might know. I spent a day in Venice, and on the way to my hotel, I passed this church that I recognized immediately. This wasn't planned, but it's the church that was in Indiana Jones and the Last Crusade. It's actually a library where they break through and they find one of the old Knights Templar who encoded the way to the Holy Grail. Very exciting for me. Maybe not very exciting for you, but I really found out when I saw that. Occupation, I'm currently an assistant professor of physics and astronomy. Maybe within the next year, depending on how my tenure case turns out, I'll be an associate professor. Recreation, well, I'll talk about some of that there. And then dreams, I would like to write a novel and I would like to go to space. And I think both of those are possible within my lifetime. Other than that, I'm enjoying the problems that we're studying in gravitational waves and multi-messenger astrophysics at the moment. And I think the possibilities, given that we're less than 10 years away from the first detection of gravitational waves, the possibilities within your career and still my career are very exciting for the next several decades. So that's me. Let me move on to the next people now. And feel free to just start talking about yourself. I think you were first, Mercedes.
Oh, sorry, I just last minute dropped another picture.
Oh, okay. Let me just refresh then. Let me refresh. There we go.
Okay, hello everyone, I'm Mercedes. Up there is my partner, Louis, and my equally lovely husband, Trey. I'll try and just kind of go through the board. So the family, I'm originally from Missoula, Montana. I have 5 siblings, so that includes me. I have 3 brothers and 1 sister. Go on. Then the occupation, I'm just beginning my 2nd year in the PhD program at the University of British Columbia. I think that has been going very fun. And then for recreation, as you can see, we love skiing. We also really love reading horror movies. I like to play video games a lot and play for some Stardew Valley. And then my husband and I are also very avid cookers. Living in Vancouver, we've gotten really into cooking different kinds of meals. So fun. There's also a lot of different things you can just eat there. The other kind of images that I put up were just some of the different projects that I've been involved in, like throughout my science career. I started out doing time series of Jani and Trojans. I have a background in extragalactic spectroscopy, and then currently I'm working on with Ingrid stairs to increase the precision, and then also looking at kind of different. Oh, not that. Okay, so that's recreation. And then for dreams, I would say, I don't know, like right now, I think my dreams are pretty limited to like one time calls. I would like to continue on in academia in general. I would like to live outside of North America at one point. That's kind of, yeah, those are that.
Nice. Thank you very much, Mercedes. We can move on then to, oh, I thought we could move on. Sora.
That my body will like so. Yeah, I can start with my family. So although I went to school, both my family is like moved. So like I'm deeply solid. Even though maybe the Southern draw doesn't come up. Occupation, yeah. So I'm studying at small board and this summer studying one-time year, but just for recreation. I feel like I never have any time. I mean, I'm pretty sure everyone. But I love to run, dance, maybe America by myself. One anime, one recreation. And in the past recent years, I picked up a lot of like graphic design. So, and then as far as for dreams, like idealistically, I like to balance like traveling the world, doing fitness, and also like exploring.
Excellent. Thank you very much. And there might be a subgroup of people that are interested in gaming and baking. So we'll see how many people that corresponds to. Are there any fans of the Great British Baking Show here? Yeah, I figured there must be some. Okay, we can talk later. Excellent. Daniel, I think, is online. Daniel, you want to go ahead?
Yeah, I can go ahead. So I did my bachelor's degree at Oklahoma State University, and I just finished my PhD at the University of Arkansas, where I primarily did LISA modeling and data analysis for extreme mass ratio in spirals. I was just offered a postdoc at Oregon State doing PTA analysis. And so that's why I'm here to learn more about pulsar timing. I've done a couple of summer schools in the past. I did one in Denmark that, Steve, you were actually one of the PTA people for. But to go to the different things, family, I am originally from Oklahoma. I have 3 siblings and 8 nibblings. And then I live with my 2 cats, Mercury and Leia. Mercury is the one on the right, and Leia is the one on the left. And I also live with my fiance, Catherine, who's a postdoc at JPL, NASA's Jet Propulsion Laboratory. And then in my recreation, I love to play video games. I love to read, specifically sci-fi and fantasy, and do a lot of outdoorsy stuff, but primarily like hiking and kayaking. And my dreams are to be a professor. So I really enjoy both teaching and research, and I would like to continue that in my career.
Excellent. Thanks, Daniel. So you're in Pasadena at the moment. Presumably you've done hiking around Eaton Canyon and other places like that.
I have. I was a visiting student researcher at Caltech for the last year and a few months, and so I've had a lot of time here to really go around and explore.
Right. Yeah, it's a great place for hiking. Awesome. Thanks, Daniel. Let's move on then to Yashvi.
Hi everyone, Yashvi, I just graduated from college, that's the graduation picture. And in terms of family, I was born in India as well as my extended family still is, but when I was like 5, my relatives moved to Kenya, and that's where like my mom and brother are. And I'm here since I had college. Just occupation, I'm currently unemployed as I transition from university to school. And that's given me actually time to do recreational stuff, like cook a lot and both the travel pictures in this are from last week, where I went to like a house in Maine that belongs to my friends, like family, and like the picture with the coffee cup, that's where like the wake up and I was taking coffee, it was like 8 in the morning down there, it was no one else, it was amazing. And in terms of plans, but I was hoping to have a smooth start to that school and hopefully a smooth back to that school because there are many bad stories, but also many good stories. And yeah, I don't think it's beyond that school later.
I understand that. So is this in PA or is this in somewhere?
That's in Maine.
That's in Maine?
Yeah.
Very nice. Very nice. Cool. Thanks, Yashvi. Nikita.
Hi everyone, I'm Nikita, I'm from India, and that's where my family is, my sister and my family. I'm currently starting my 3rd year as a PhD and recreation, I discovered about that and doing that. Some of my plants at the bottom there. I really enjoyed that as well. My dreams sort of overlap with my occupation and recreation. I just want to keep on contributing and doing okay practical things. And I hope to travel the world as much as possible. In the bottom center over there is the Shenandoah National Park in Virginia, which I visited last week with a couple of friends. And the picture at the bottom right is from India, where I was a month back visiting family. So there's this place in North India called Dharamshala, which is famous for its monasteries and Buddhist religion. Yeah, and one goal I have for the coming 6 months is to get married.
Awesome.
You name your plans.
Hmm.
Not yet. Okay. You wanna-
Is that just in case they don't make it? I can't keep plants alive. Someone, a student here actually bought me a succulent because I have fake plants in my office. They said, I have to buy you a real plant. It's very easy maintenance. You can't kill them. I killed it. I can't keep succulents alive.
No, that's fine.
Yes, I guess so. I guess so. Thanks, Nikita. Sophie.
My family and myself from Virginia, so that's where my family is now. My father actually British, so sorry.
That's it.
And I'm currently an undergraduate, which I guess kind of means unemployed. I did my senior year at Berkeley. And for fun, I really like old man hobbies, like bird watching, doing puzzles, and reading a lot.
Yeah.
I started getting into hiking after I moved out west. And in terms of dreams, I'd like to get into graduate school and at some point see the Northern Lights.
Did you see any of the Northern Lights recently when they came back? Oh. So they technically were visible down here, but not. I wasn't able to see it with the naked eye. With the camera, let's see it. Excellent old man hobbies. Yeah. Try doing jigsaw puzzles and watching Murder, She Wrote. That's a great old man hobby. If you've not heard of Murder, She Wrote, I'll let you discover that for yourself. It's fantastic. Did you talk about Bub, your cat?
So he's in Virginia as well.
Nice.
He's pretty shy. Okay. Sorry. The top right is Shenandoah National Park in Virginia. Where I'm going with my family, and then the bottom two photos are from the trip to Monterey that I just did. In Santa Cruz that I just did with my boyfriend, and that's me at a restaurant. She's the first.
Nice. But Bub still fits in that box, so yeah. Yep. Levi's not here at the moment, and Levi I don't think is online, but Levi, she's currently traveling back. Everyone in my group, to various extents, has been affected by a travel curse. Nobody has yet escaped coming back from the IPTA meeting that has not been delayed. So Levi, I think, is currently on a Greyhound bus coming from Virginia at the moment. But I'm sure she can introduce herself to you at a later date, probably tomorrow. But Levi is a rising third-year student, just passed their quals here. And was also in Venice, as I can see. Rogero.
Yeah, so I am Joe, and I come from the Northeast from there. Yeah, more this there. Yeah, I'm doing my PhD at API, which is the University of Rotterdam, and Maastricht, which is the Netherlands Institute for Radio Astronomy, developing the state from there, while the Baltimore is me on the side. I couldn't find anything better. I love playing football. I should say soccer here, I guess. You can see, well, I didn't find a picture of myself playing, so I just found myself celebrating for eagerly. That you can see on the bottom. I also love playing chess, and I took a picture of me playing, but not enough, because that helps you always die instead of so, and yeah, I also love watching movies, cooking, and I'm always happy to travel to restaurant. That's my recreation. My occupation, I see that one said I want to be a teacher, and finally get dreams. And I the thing that come up for my most is really United States.
Were you traveling here during some key matches?
Kind of no.
Okay.
I missed that one race and it's for the front and it's
Okay.
all of this.
Yeah. Yeah.
But tomorrow I might be distracted with it, yeah, saying.
What is it tomorrow at 2 p.m.?
2 p.m. is France.
Ah, okay. Well, maybe we can set up a little monitor in the corner.
I'm not saying.
Is that Dwingaloo? Is that Westerbork?
Right, yeah, yes.
Very, very, very quiet there.
It's
Peaceful.
no civilization, I think is the best.
Right, except horses. There's some horses and cows.
Yeah. And a lot of, any kind of animals that don't means.
Right, right. Excellent. Okay. Kyle?
Hi everyone, I'm Tyler as well. I have one cat you can see on the bottom left there. A 2-year-old kitten now, so she's gorgeous and lovely. I have parents now live in Florida, but I actually grew up in the Pacific Northwest, just worked in Seattle. That's actually still where my brother and many of my closest friends still live. My occupation, I am, well, a rising 4th year now, which is scary to me. I focus mostly on the quintus statistics for PTAs, but I do a lot of Bayesian statistics. Don't think I don't do that. For recreation, I do plenty of video gaming. Some of my favorites are the Monster Hunter series, and then I've also recently gotten into Street Fighter. And surprisingly good at that. I also tend to do astrophotography, so the bottom middle picture there is a picture of the Orion Nebula that I took. I also got to see the eclipse this past year, and then also I just so happened to be in Washington at the time that the northern lights were really, really strong, and then really far south. It was very visible, so I'm really sorry. And for dreams, I mean, I love the Pacific Northwest, so once I finish my PhD and after I get at least a couple more papers in, I'd love to go back, but not that I'm getting anything done.
Nice.
Future we'll figure it out.
Now, is this modern Street Fighter or is this 1990s Street Fighter?
No, this is the new stuff.
I can't relate. I can only relate to 1990s. All the characters must be the same though. It's all Street Fighter. Okay. Just better graphics. Kyle.
Hi, I'm also Kyle.
Also Kyle G. 2 Kyle Gs.
Also raised a senior at Oregon State University. I am the youngest in my family. I have 2 siblings, older brother and sister. They're all from Silent Oregon. They're 800 size now, they're small. For occupation right now, I got a scholarship to do research with different capacity on some PTA noise analysis stuff. Recreation, I just like to hike, read, just be outside every. And my dreams are to get into a PhD program in universal analysis.
Nice. Thanks, Kyle. Mateo?
I'm a basic here at Oregon State University. Currently, physics major and well, studying physics. Right now, all I'm doing is for full-time is all the people learning from Harvard for last year. I've grown Oregon State, which is very close to Florida. And during the time, I like
Nice. And searching for pulsar candidates is how a lot of people probably here got started in PTA. So it's a good foundation to build up something else. Well.
No, it's my name is Jani. So I'm from the Laker Republic. That's where most of my family is, my mom and dad, my brothers in Tallahassee, Florida. Occupation, I'm a postdoc here, a postdoc at Princeton University. And I mostly do observational photography, mostly do of our libraries, security wider libraries in particular, very interested in global clusters, configuration of our clusters. My favorite was their ABC 67. Recreation, I also love chess. There's a chess night at a local bar called Villager that I love. If you're over 21, like chess, you should join on Wednesdays. Dancing, I'm very good at it, but I know salsa and bachata and watching sports. I'm not most of the thing, but because American, I like baseball and I'm all of sports, so welcome to
Did you say dreams already?
Sorry?
Did you say what your dreams were?
a job that I like, stable community, the city that I like, very people, very.
Yep. Good dreams. A permanent job, the Holy Grail, yeah. Excellent. Keen?
I'm also from Oregon State University, going to my senior year of physics undergrad. I recently added on a engineering minor and math minor. I'm from Washington, around Seattle, Auburn, between Tacoma and Seattle. For my occupation, during summers, at least for the last few summers, I've been working at a concert venue up in Washington. Recreation, I like to hike, I like to work out, I like to play video games, and that my girlfriend, I like to read. For dreams, right now, my dream is just to get into grass.
It's a very good dreams. I appreciate that everyone's dreams are like, just want to get to the next stage. And I really get that. I really get that. Thank you very much. We've got like an Oregon State block here. This is quite the, yeah. I'll have to thank Javi and Jeff for sending you all along. Celia.
Hi, I'm Cyril. I'm originally from New York. My native family is from New York. Most of my family is Ecuador. Occupation, I'm a second year grad student in the technical grade program. And I will speak on zoning and specialty and coordination in the gravitational program, and the national management gravitational protection. For fun, I like reading, baking, volunteering, observatory, and activities. I also look out for crossing, started out. I guess we should come back, I like the university, graduation, and that's observatory that I used to volunteer / work at in Chesapeake, New York. And then that's my fiance, Barbara, and our cat actually, he's really tries to, That's a picture when we first off.
That's the catio, is it? In Nashville? That's the catio. Do you want to, I can't really describe what the catio is, but.
The cat cafe, and just kind of build it and then talk to cat all about the wall, and if you don't really want the cat,
So it's a cafe where you probably will get emotionally blackmailed into getting a cat. Yeah, I bet. So if you want to get a cat while you're here in Nashville. Oh, did you say dreams?
Oh, okay, I want to finish my PhD, my PhD, I love your special M.A. It's a job market. And I think it's nice business, I would love to have a homestead / farm one day, I want cows.
I like that dream. That's, yeah, to build a self-sufficient compound. Jose.
I am originally from San Pedro Sula, Honduras. My family, my parents and one of my 3 siblings are still back home, but then me and 2 of my other siblings are here in the US. Went to undergrad at Virginia Commonwealth, go Rams, And, yeah, currently a second year graduate student at the Vanderbilt Bridge program as well. I'm working with Dr. Descansi and Dr. Smith in the math department doing, linear scalar waves from black hole backgrounds. So kind of like the 4-man's linearization of what we're doing today with gravitational waves, like the math analysis of that. And, yeah, a couple of hobbies of mine, I'm really into coffee and mixology. I also, yes, I'll get to that in a second. I really enjoy volleyball. I really enjoy jazz. So whenever there's live jazz music, you will probably see me there. I shop at Costco a lot to the point where some of the people that work there let me in without showing my membership at that point. And I love playing billiards. Yeah.
Very nice.
So the picture is my fiance and I, and that is Nemo, also called Professor Nemo. As you can see in the picture, he's very well versed in math. He helped me out with my homework. Yeah.
Excellent. Dreams? What are your dreams?
My end goal is to become a faculty professor. So that is one dream. So at some point I would like to have a bar, cocktail bar.
Physics themed? Or just a bar?
Personal.
Okay.
Whatever the market tells me is gonna actually be profitable.
Smart. That is a smart answer. Right, excellent. If you like mixology, do you know the cocktail that I had in my picture earlier? It was a Vesper martini, which are very good. Nima.
Hello, everyone. My name is Nima. I am a VITA postdoc here. I didn't really memorize what VITA stood for, but it's Vanderbilt Initiative in Data Intensive Astrophysics, which is exactly what I do. I look at noise all day and I try to just make sense of it. I made these images smaller.
Maybe let me move some things around. Oh, that's better. There we go.
Okay. So I'm part of this VIPER group here at Vanderbilt. About the things that I like, I really thought about it. Really haven't thought about this for a while. I think I love physics. And now it's my job. I used to play soccer. I love soccer. Video games has always been part of my life. I love cars. I think I love my car more than I love myself, which is not good. That's why I'm going to drive it. I love building computers. It's a very expensive hobby. Unfortunately, I can't do it every day, but I wish I could. That's the picture that you're seeing. Those lights are coming from my computer. I made it a lot cleaner. I don't know how much of it you can see, but it's one of those gaming PCs that are connected with tubes. This is my last TA salary that I got from Oregon State. I forgot to say I graduated. I have a PhD from Oregon State University. I work with hobbies. So the last salary I dumped it all in the computer. It cost me north of $3,000. So this is well, the picture that's obviously me, the bottom left. That's the game that I love the most, God of War 2, it was released for PS2 15 years ago, maybe no longer than that. I will always remember that game. That's my brother's dog. He is just funny. I don't know why he looks like this, but he's normally sleeping and he's trying to be a bear. And the person in the right corner, if you are familiar with soccer, that's R9, the Brazilian striker. I think he retired 10 years ago, but
at least 10 years, right?
At least 10 years. I used to watch him when I was sick, and that's why I played soccer, because I wanted to be like him, nowhere near. But
in spirit.
At least I tried. Yeah, I had all these shirts.
The Ronaldo of physics.
Yeah. The other thing about it is he's wearing Barcelona's shirt, which is my favorite soccer club. Um.
What are your dreams?
Dreams, there's no point in having dreams, if I don't have any.
That is the most Nima answer to that.
If you don't get your dreams, that's obviously bad. If you get your dreams, you get greedy and you want more.
This is like philosophy now, but thank you. Yeah. Or is it nihilism? I don't know. Yeah. Atika.
Handwriting. I'm a parent and one older brother. They all live English. My wife is with me in Japan. I did a master's at the University of Town and started a PhD. Returned topic. And then master's, I did a master's in University and now I'm the PTA in Japan. So that's my career and program on the lockdown. And so this has to one over. There's very right from that.
Oh, this is Maria's figure?
Yeah. And you can see the photos that when you go to the stairs, that I'm there around 300 or more stairs to get there. I like to go into the sometimes so that I can learn how to speak. And my wife loves to hike, so I can just go with her, and that is how I live like a.
Yeah.
About dreams, probably I agree.
It's interesting that the people interested in alternative gravitational polarization don't believe in dreams.
Like religious, I have to learn from my account. I always just do this all again right there.
All right, so we've got potentially people to go to play chess.
That's all.
Excellent. Thanks so much. Mohammed is possibly online.
Yeah, hey everyone. I'm Mohammed. I'm a second year PhD at Vanderbilt. I graduated with a physics degree from Brandeis University in Boston. Currently, I'm studying gravitational waves from exotic phenomena, such as hypothesized wormhole black hole interactions. In my free time, I usually play basketball or I'm just working out. Or recently, I've been reading a few books as well, which is like a new hobby that I've picked up. My family is in Canada. I've got two sisters and one brother, and my dream is to do hopefully good, impactful research in the future.
Nice. What kind of books are you reading at the moment?
Well, right now, I'm reading this one book by Fyodor Dostoevsky, who's like a pretty popular Russian writer. It's called The Brothers Karamazov. It's like pretty popular.
Yeah, it's right. Yeah, it's right.
Kind of a hard read though.
Yeah, it's kind of bleak as well, but it's a very, very famous novel. Is that the only thing on your reading list at the moment, or do you have something a bit lighter?
For now, that's the only thing. Once I finish this book, hopefully I'll move on to like.
Nice. That's the kind of book where it can be a project in itself to make your way through. I agree, it's kind of difficult. All right, Angel.
A right senior economy and physics major at Boston University. My family are immigrants, so I'm a first generation student. I like, most of my family is in South Florida, which near the Miami area. I think that's it for family. Occupation, Stephen from the Boston University. I spent 2 years studying wave projects with the radar group. currently I'm working with, Dr. Taylor and, Kyle on, like determining thresholds for, the use of pairwise covariance. Gravitational force stuff. Yeah, for recreation, I mostly play Pokemon, also, I'm really into anything comic book or superhero related. And I also watch anime too. My favorite game of all time is Earthbound. If you guys like RPGs, it's a really great one. It's super old game. It's fun. And as for my dreams, I want to graduate and get into grad school, and then also hopefully write my own comic book.
Nice. And who's this?
Oh, yeah, okay. So, okay, both, okay, Father Right Picture, that's my dog, Nico, he is a little old now, he's like 8 or 9, we don't know who was the rescue, we just, we just know that when we got him, he was about 3 or 4. But he's great, he's fun. Top left picture is me presenting the work that I did last summer, working with the laser agents. Picture on the top right is me. Bottom left is the view from the top of the College of Arts and Sciences at Boston University. That's one of the few perks of astronomy in town over there is being able to get on the roof. And it's, though it's not too visible, that dark picture there is of the night sky in Flagstaff, Arizona, where I went this spring break for observing using a telescope that you own there, but it was cloudy every single night except that one. But yeah, and also you guys have noticed I have a thing on my head. I'm okay. I ran into a tree last night and it was not hurt.
Newton just let an apple fall on his head.
Yeah.
But you ran into a whole tree. Yeah. Thanks, Angel. Adja? It's Adja
Hi,
online. There we go. Yep.
hi everyone. I'm Adya, and I'm a second year PhD student from IIT Roorkee, India, which is in Uttarakhand. And I must say, Uttarakhand is a beauty. If you visit India, you must visit here. It has the mighty Himalayas. So I have recently started traveling a lot. So I urge you all to please visit. I'm working with Professor A. Gopakumar, who is my co-supervisor from TFR, and I have been working with the Indian Pulsar Timing Array for a year now. My main interests include pulsar astronomy, binaries, and especially the search for the gravitational waves. Hoping to get a pretty good signal very soon through PTAs. So, as a child, I have loved looking at the night sky, whether it be a full moon or a new moon. So full moon for the obvious reasons, and new moon also shows us all the different constellations and the stars. So I love stargazing. I would like to say that in short. Apart from that, I like to read books too, although I have a lot of half-read books in my collection. Currently, I'm reading the book called Forest of Enchantments. If anybody knows about the Ramayana here, so it's this book tells about the story from the female protagonist view. And yeah, as far as my dreams are concerned, I would definitely want to become a good professor one day who can maybe ignite the fire of um, to for the night sky in some other child who was just like me. And secondly, I would really love to travel the world with my partner. So yeah, that's about me.
Wonderful. Thanks for joining, Ajit. Okay. Edith?
Hello, am I audible?
Yes, we can hear you.
Hi, so my name is Vidit and I'm also from India. I'm a first year grad student at TIFR and currently I'm just doing my coursework. Well, I've also started a project with Gopu, uh,
And as far as my hobbies are concerned, I absolutely love football. I I can see that I breathe football. I am still following Euros 2024, which I'm following like right now. I watched all in the entire matches, even when my exams were going on over here. I could not stop watching football at all. I actually play lots of sports. I play table tennis, I play badminton, I play football as well. I play cricket as well. And in my free time, I love hiking. I tried kayaking recently, which you can see. And I also have a pet dog named Katie at my home, and she like craves attention. She can't tolerate attention on anyone else except her. And as far as my dreams are concerned, well, they're very football oriented, obviously. I would want to visit Barcelona one day and watch FC Barcelona play at Camp Nou. I would want to meet Messi and Neymar at least once in my life. Yeah, that's about it. That's me.
Thank you very much, Vidit. So we've got a couple of Barcelona fans here then, competing for attention. Excellent. Thank you very much. Let's move on then to Aman. Is Aman online? Maybe not. It is very, very late in India at the moment, so I completely understand. So we can move on and maybe get to know Aman later. Atarva, similarly, probably pretty late. William, another being struck by the Vanderbilt travel curse. But William is currently recuperating in Nashville at the moment, and you'll meet William tomorrow, so he can introduce himself tomorrow. Oh, there's social information. Come with us to Centennial Park on Saturday night for a night of live big band swinging. Okay, so you've got your Saturday evening planned. Big band swing is on Saturday night at Centennial Park. Centennial Park is right adjacent to campus. So William can direct you there. I guess this is him hiking recently in, that's the Dolomites, right? This was from the IPTA meeting that happened recently. And the top left structure appears to be a cat that's swirled. That's a wiggle worm. All right, Robin?
Hi, so I'm a fifth-year graduate student at Oregon State. I work with Tommy Stevens on gravitational wave detection methods, and my current project is trying to detect stochastic gravitational background with minimal PTA to get away with. So for family, I have parents and a sister. They all live in San Diego, where I'm from. The top picture is the beach that I frequent a lot when I'm down there. For all that. Yeah, so I got my bachelor's from UC Santa Cruz. I did research in observational like supernova stuff. Great results. It's actually pretty cool. So for hobbies, I like to bodyboard and surf. One of those pictures of me right after one of the sessions. I play guitar. I play D&D. I actually dungeon master most of the time because no one wants to learn the rules. So if anyone wants to play, I learn. Video games, and I recently picked up golf. I am very bad. I shank every shot I can, not on purpose. And so for dreams, I would say I want to finish my PhD, and if I can find some way to keep doing this research in San Diego. Thanks.
You see San Diego is really good. Who's this?
Oh, that's our family dog in San Diego. He's a pit bull lab mix. He's pretty old now, about 14 years old.
Mm-hmm.
Yeah.
Nice.
Awesome. Take a picture of him.
Yeah, it looks like it was an action shot where, yeah. Yeah. Thanks, Robin.
Hi, I'm Alberto. Just call me Albert. I'm a second year graduate student at Oregon State University. I'm currently working with Jeff Allen, trying to find something in quasar noise curves, something interesting maybe. Using, instead of gravitational waves, trying to find some EM signatures so you can do some targeting, maybe. Who knows? Family, I didn't update for this, but family, I'm from South Texas. I have two little sisters, both of them down there. Occupation, second year graduate student. Although I am technically unemployed at the moment. That's pretty nice. The reason I'm here is because I saw like explosions when I was little and I never stopped, like, what's the bigger one? And like, I've worked my way up the energy scale, like chemical and then electromagnetic and then non-nuclear. The government is a little sensitive with that. But then, stars and variable stars, that's me, at McDonald Observatory, that's like 150-year-old telescope. It's way bigger than the book, actually. That was fun, my observation was there. I think 1.2 years. Yeah, it's enormous. But yeah, hobbies, recreation, I like to mention slightly smaller energy phone. That is a very janky and horrifically unsafe Tesla coil that I built. Thing. Yeah, don't do that. Dreams, I think.
What did you do with it?
I made it speak for a brief moment, and then it broke. But yeah, I could pass. I don't think anyone's actually done that specific kind of design. Most Tesla designs you do bursts, so it's got that really horrific high frequency like ring at the end of it, and I didn't want that. So instead, I drove it with a vacuum tube that I got off a very sketchy Russian website.
This has been recorded, so.
Yeah, that's what I do out of school. And dreams, I guess, would be to make a plasma that emits enough radio noise to the FCC to come knocking.
That's a good dream. That's solid goals. Thanks, Albert. David was here but had to leave. You can hear more about David tomorrow, working with professor here on cosmology and cosmic strings. Sparrow.
Hi, everyone. My name is Sparrow. I am recently graduated from the University of Wisconsin in Milwaukee, and I'll be starting a PhD program in Swinburne weeks. My family is originally from the Milwaukee area of Wisconsin. I live with my partner in Utah, out in the Rocky Mountains, which no move for Wisconsin. So my occupation right now, since graduating, I've been working at the planetarium in Salt Lake City, where I do like education, public outreach in the community, and it's been really enjoyable because I get paid to infuse about science every day. As far as recreation, I have some transparent PNGs of little guys from games that I like. The Neutron Star is also a transparent PNG little guy from a game that I like called Elite Dangerous, which is a galaxy themed sandbox explorer thing. As far as my, I don't know, other recreation, I like to cook and eat food and play board games. And then my dreams would be if I could have a future where I could to be at the edge of knowledge of astronomy. I think I would be very happy. I think the closer my life gets to being a farming sim video game, the happier I feel. And I think professionally, I'd really like to participate in creating better, more accessible, and more enjoyable physics and astronomy education materials.
Very nice. Some incredible hobbies here as well. Metalsmithing and longsword fencing. So longsword is, how's that different from a broadsword? Is that synonymous with the broadsword? Like a gigantic.
This might be something that's probably at least 48 inches in length. It's made out of steel, and it's thin.
Mhm.
So if you think of like traditional fencing with like the rapier, it's quite similar in form, but
Okay.
different.
Awesome. That's really cool. Who's this? This is just another character, yeah.
The one on the right is a pink sheep from Minecraft. And the cat in the picture is my roommate's cat named Mister, who likes to sit on my laptop that gets very warm while I study.
They all do. They all do. Great. Thanks, Farah. Aaron.
That's me. I'm also. So. Since I got out of school and we're on a lunch, I have a lovely dog of mine. You can see there, she's super cute. I also like mountains at no beaches, and I hate humidity. I just have to say that because I was talking about it.
Yeah.
Let's see, family occupation. Yeah, all the rest of my family is doing this. Really big fan of this one because I actually just saw them. The weather there, much. Occupation, I work here on the post spot. This is one touch start. One just as a postdoc researcher just now. This will be my third year as an staff fellow here at Vanderbilt. Recreation. Sad for Angel, he just left. One of my recreational things is I actually buy way too expensive old Super Nintendo games. So I actually probably wear them. Bars. Yeah. Yeah. Super great. Yeah. That's one thing I do. I like reading fantasy books. I also live in dragons. I'm sorry that you only overread this. Oh, great. Pretty proud of that. No, but I didn't, but everybody else did. Let's see, entries. Honestly, my dreams feel very basic. No, it's just a little standard. I actually like all and really besides that, you know, there's the standard, like, I like that financial stable job. That's all mostly it.
Yeah. For dreams, no one has said world peace yet, but I guess that's okay. Nick.
I'm born and raised in Los Angeles. That was there. So that was like I'm married. Right now, she goes to law school in San Diego, as well as State, so it's driving back to San Diego. Yes. Occupation, I'm second year, master's student, I work with Brian, right now, I'm working on machine learning, I'm trying to teach it. A lot of issues. And for hobbies, like about 3 weeks, so they kind of cooking, steak, jazz, and immigrants, crazy into meat sauce, you know, almost surrounding. And
What are meme stocks? I know what memes are, but what is meme stocks?
So basically, like the next page of the game. That was and then you have to start to see and then also.
So this was accurate. 3 digits of pi. 3.14. Yeah. Well, that's. I mean, that's. Excellent. Thank you, Nick. Tyler, is Tyler still online? Yep.
I'm still here. Hi.
Who's internet famous? Yeah.
Hi, I'm Tyler. I'm a PhD fellow at NRAO in Socorro, New Mexico. In the last year of my PhD, I'll be applying to postdocs this fall. So if you have one of those, I'd really like one. I work with Paul Demarest on pulsar population synthesis and optimizing our strategies for detecting gravitational waves with PTAs. So, you know, how can we make the best use of our current telescope resources and future telescope resources like DSA 2000? last year I started a YouTube channel making educational astrophysics videos in support of the gravitational wave detection. The clip on the right is a clip from one of the videos, how to dance like a gravitational wave. And I just like doing outreach in general. For fun, I love rock climbing and hiking. New Mexico is a great place for those things. I also like making hot sauce. For a while, I was trying to make the hottest hot sauce I possibly could out of New Mexico chilies, a pursuit which I was recommended to abandon by my doctor. And I like making pizza. I'm from New York. New Mexico doesn't have any good pizza. So I had to figure out how to make my own. Dreams refer back to the job part. In particular, I'd really like to continue doing the outreach stuff somehow as, part of a postdoc or sort of future career pursuits. Yeah.
Thanks, Tyler. This GIF is strangely hypnotic. I think it's lulling us all into.
Yeah, I didn't really think about the fact that this was just going to play continuously while the slide was up.
So you make hot sauce. I like watching hot ones. Where in the progression of the hot sauces and hot ones do your hot sauces fall? Towards the milder end, or do you go really to the highest heights?
I would say probably somewhere in the middle. Definitely not like the bomb level. Like a lot of the really the hottest ones they have on that show are either made with chilies that are not accessible to the general public or with like extracts. Mostly I use New Mexico chilies, which sort of the hottest ones kind of fall around like ghost pepper range.
Okay, very cool. Thanks, Tyler. And I think we're at the end. So thanks, everyone. Give yourself a round of applause. So the next thing
Please take me off the screen.
Done. The next thing we can do is, if you feel like you'd still like to get to know each other, we can try some speed networking, where what's a good time? 3 minutes? We 4 minutes. I don't know. What do you think? 3 minutes or 4 minutes? 2 minutes? 3 minutes. So the idea would be to just rotate around and talk to a new person every 3 minutes. There are some questions that I've personally come up with to help seed the discussion and break the ice. The questions I have, I'll put them up on the board, but let's see, where did I put this? So, favorite Nicolas Cage movie, the correct order in which to watch the Star Wars movies, and after a year of distance from the crazy PTA summer of last year, were PTA's Barbie or Oppenheimer? Those are your 3 icebreaker questions. I'll put them up on the board. Maybe we'll play some music in the background. See, it's gotten you talking already. That's perfect. The good thing is all of these have correct answers. All right. So if you're sitting, stand up and go and sit somewhere else. Move around, randomly talk to new people, ask questions, get to know each other. I'll tell you when to stand up again.
I don't want to talk about stage. What's your favorite house? I did. Yeah, I feel like having something. You know what droplets are gonna came in? Yeah, that's very. It is. It is basically the John Blake and it comes out.
Yeah. Nihon's now mine. I have to actually use it for anything.
I've seen the specs on these. It's not that good.
No, it's perfectly useful for just like your desktop, answering emails and stuff. And it's talk to someone new, change people to talk to.
Mine has an HTML.
I mean, it's good for something like this. Where you just see like All right, everyone. I think everyone is networked out. I'm going to turn off the elevator music. All right. Well, it got really quiet all of a sudden. So I think everyone is networked sufficiently. Everyone at least got talking to each other. But if you're wondering what to do right now for a drink or for some dinner, I heard some people talking about Hattie B's. If you want to go to that, it's a 20-minute walk away. Might not be too busy. I could probably check to see how busy it is right now. What do you say? Oh, okay. So yeah, it says it's a little busy, but it's going to be like that for the rest of the evening. Alternatively, I was going to go to some place nearby for just a drink, and it's called Jack Brown's. It's about a 7-minute walk away from here. Yeah, so it's super easy. You would just come out of this building, turn right and turn left again. The place is called Jack Brown's. There are a couple of other places nearby, but if you just want to go and hang out for a little bit and have a snack or have a drink, feel free to do that. If not, then we'll start at 9:30 tomorrow for the first lecture / tutorial. But if you want to come a little bit early and get some coffee, stuff will be here from about 9 o'clock. Really, you could probably come as early as you like, but we'll be here from about 9 o'clock. So that ends today. Thank you so much, everyone. It's been a fun first day. Software installation took like no time at all, which is the first that's ever happened. So if there are some people that want to go to Jack Brown's, I'll be walking over there now. If not, have a good evening. See you soon. Yay.